What stars do when no one is watching. There is something happening above you right now that has been happening for longer than the Earth has existed, and it will continue long after the Earth is gone. It does not require your attention. It does not require any attention at all. In the darkness beyond the ceiling, beyond the atmosphere, beyond the thin blue shell of air that holds this world together, stars are burning. They are fusing hydrogen into helium in cores of inconceivable heat and pressure. They are hurling light in every direction through the cold of space. They are living their long lives, some of them hundreds of times longer than the life of our own sun, in perfect, indifferent silence. They were doing this last night, while you slept. They were doing it 10,000 years ago, when no human eye had ever turned toward them with understanding. They were doing it 4.5 billion years ago, before this planet existed, before the cloud of gas and dust that would eventually become the Earth and the Sun had begun the long gravitational collapse that would bring everything you know into being. The stars do not need to be watched in order to do what they do. They do not notice whether they are noticed. They simply continue shining, fusing, living, dying, in the great quiet of the universe, whether anyone is looking or not. Tonight, you're going to spend some time thinking about what they're doing up there in the dark. Not in the way of a telescope, not with effort or with straining to see, but in the way of drifting thought, the kind of thinking that happens at the edges of sleep, where ideas become more like feelings, where the size of things softens from something alarming into something almost comfortable. The universe is very large, but you are very warm, and the stars are very far away, and there is something reassuring, in the end, about the idea of so much happening so quietly, so far beyond anything that requires your involvement. The light of the nearest star beyond our sun, the small red dwarf Proxima Centauri, takes 4 years and 2 months to reach us. When that light set out on its journey, you were perhaps 4 years younger. Perhaps you were in a different place, living a different version of your life. The light did not know this. The light simply traveled, at 300,000 kilometers per second, through the empty cold of interstellar space, making no adjustments for what it might find at the end of its journey. It arrived at this solar system, crossed the distance from its edge to the position of your planet in approximately 8 more minutes, filtered through the atmosphere, and ended, or would have ended, had the sky been clear and had you been outside to receive it, at your eye. This is where every starlit night ends. At the eye. At the body lying in the dark. At you. Tonight, over the course of the next few hours, the story of the stars will unfold in layers, from the moment of their formation in vast cold clouds of gas and dust, through the extraordinary physics of nuclear fusion that keeps them shining, through the long journey of light from the stellar core to your eye, through the surfaces and spectra and variable rhythms and companionships and deaths of stars, and finally back to the stars that are overhead right now, doing all of this, in the silence and the cold, while you rest here in the warmth of this room and the world turns slowly beneath you. There is no urgency here. There is no test at the end. The information, if you retain any of it, is simply the residue of a pleasant journey taken in the direction of sleep. Most of what you hear, you will have already forgotten by morning. This is not a failure. This is the nature of the threshold you are approaching, the place where understanding becomes sensation, where facts become the texture of a dream, where the immense and ancient machinery of the universe is no longer something to be grasped but simply something to float in, the way you float now, in the warmth of this bed, in the dark of this room, on the surface of a small planet orbiting an unremarkable star near the outer edge of one galaxy among 2 trillion. You are very small, in the most beautiful possible sense. And the stars are very old, and very busy, and entirely unconcerned with the passage of your evening. Let that be a comfort. Rest now, and listen. Chapter 1: The Birth of a Star. A star begins in cold and darkness. Not the cold of a winter night, which is merely the absence of the sun's warmth at a particular angle and distance, but a cold so deep and so thorough that it surpasses ordinary language, a temperature of just 10 or 20 degrees above absolute zero, the theoretical floor of coldness, the point at which molecular motion nearly ceases entirely. In this cold, in clouds of hydrogen and helium gas drifting through the space between the stars, the long process of stellar birth begins. Not with a flash. Not with any event that could be pointed to and named the beginning. But with a very slow, very gradual thickening of gas in one region of the cloud over another, a slight excess of density, a tiny gravitational advantage, and then, over millions of years, the quiet assembly of a star. These clouds are called molecular clouds, and they are among the largest structures in a galaxy. The Orion Molecular Cloud, which lies roughly 1,300 light-years from Earth and is the birthplace of the stars you see in Orion's sword when you look at that constellation on a clear winter night, is roughly 240 light-years across. It contains enough gas and dust to make hundreds of thousands of stars the size of our Sun. It is cold and dark and largely invisible, detectable not in ordinary light but in radio waves and infrared, where the faint emissions of its molecules can be measured. Within this cloud, in regions where the gas is slightly denser than average, gravity is quietly winning its long argument with pressure. The process by which a gravitationally unstable region of a molecular cloud begins to collapse is described by a condition worked out by the British astronomer James Jeans in the early 20th century. When the gravitational potential energy of a region of gas exceeds its thermal pressure, when gravity, in other words, is stronger than the tendency of the hot gas to push outward and resist compression, the region will begin to contract. As it contracts, it warms. As it warms, the pressure increases and resists the collapse. For a time, the two forces are nearly balanced, and the collapse proceeds slowly. But in a cold molecular cloud, the heat generated by the initial compression is radiated away by the gas molecules, keeping the temperature low and allowing gravity to continue to win. The collapse accelerates. As the cloud collapses, it does not fall uniformly toward a single point. The cloud has some slight rotation, some very faint angular momentum imparted to it by the turbulent conditions of the galaxy, and as it contracts, that rotation increases, just as a spinning ice skater speeds up when she pulls her arms inward. The collapsing cloud begins to spin faster and faster, and the rotation flattens it into a disk, with the densest and fastest collapsing region at the center and a surrounding disk of gas and dust that will eventually, over millions of years, form planets. This is the protoplanetary disk, the raw material of a solar system, wrapped around a young star that has not yet ignited. The central concentration, the protostar, continues to collapse and heat. It cannot yet fuse hydrogen in its core, the temperature is not yet high enough. But it is already glowing, heated not by nuclear reactions but by the release of gravitational potential energy as the infalling gas is compressed. It is a warm, puffed-up object, perhaps 10 times the radius of the final star, radiating light and infrared energy, surrounded by the dense disk of material from which it is still accreting. During this phase, many protostars produce spectacular bipolar jets, columns of gas accelerated to thousands of kilometers per second and launched in opposite directions along the rotation axis of the disk. These jets can extend for light-years from the protostar, carving structures in the surrounding cloud that are visible from Earth as narrow, glowing streaks emerging from regions of star formation. The Pillars of Creation, that famous image from the Hubble Space Telescope, 3 towering columns of dark, dense gas rising from the Eagle Nebula 7,000 light-years away, are regions where the gas is dense enough to resist the ionizing radiation of nearby hot young stars. Within those pillars, new stars are forming right now, shrouded in the dense cocoons of gas from which they emerged, as yet invisible to optical telescopes. The pillars are, in a sense, the nurseries of future solar systems, regions where the same process that created our Sun is underway, in the cold and the dark, exactly as it has been for the entire history of the galaxy. When the contracting core of the protostar reaches a temperature of approximately 10 million degrees Kelvin, a threshold that seems impossibly high and yet is achieved through the simple mechanical process of gravitational compression, a transformation occurs. At this temperature, the nuclei of hydrogen atoms are moving fast enough that when they collide, something can happen that would be entirely impossible under any conditions found on Earth. Two protons can approach close enough to each other for the strong nuclear force to reach them, and fuse. The fusion reaction ignites. The star is born. This moment, the ignition of nuclear fusion in the core of a new star, is not visible from the outside. There is no flash, no sudden brightening that an observer could see and identify as the moment of birth. The transition from gravitational contraction to nuclear burning happens deep within the star, beneath layers of gas thousands of kilometers thick, and its effect on the surface brightness is gradual. But something profound changes. Before ignition, the star was shrinking, falling inward under gravity, with the only resistance coming from the thermal pressure of its heated gas. After ignition, the energy released by fusion heats the core and creates an outward radiation pressure that exactly balances the inward pull of gravity. The star stops shrinking. It settles. It finds its equilibrium. And in that equilibrium, it may remain for billions of years. The time from the initial collapse of a cloud fragment to the ignition of fusion on the main sequence varies enormously depending on the mass of the resulting star. A star like our Sun takes roughly 50 million years to reach this point, a span that is brief by geological standards but longer than many entire dynasties of life. A very massive star, perhaps 20 or 30 times the mass of the Sun, reaches ignition in as little as 100,000 years. A very small star, a red dwarf, with perhaps 1/10 the Sun's mass, may take a billion years to contract sufficiently to ignite. The pace of stellar birth is calibrated not to any human sense of urgency but to the patient, enormous rhythms of gravity and heat. The young stars that emerge from molecular clouds are often gathered in clusters, open clusters, loosely gravitationally bound groups of tens or hundreds of stars that formed roughly simultaneously from the same cloud. The Pleiades, that compact bright cluster visible in the constellation Taurus on autumn and winter nights, is an example, a cluster of hot, blue-white stars about 400 light-years away, perhaps 100 million years old, still young enough to be wrapped in wisps of the gas cloud from which they formed. Over time, the cluster's stars will drift apart as the gentle gravitational tugs of passing clouds and the differential rotation of the galaxy pull them in different directions. Our Sun was almost certainly born in such a cluster, its siblings long since dispersed across the galaxy. We do not know which stars they are. Somewhere out there in the dark of the galaxy, the siblings of the Sun are shining. They were born from the same cloud, at roughly the same time, nearly 5 billion years ago. They carry the same chemical composition in their interiors. They may have planets. Some of those planets may have conditions suitable for life. None of this is known. The siblings simply continue their lives, wherever they are, unseen and unidentified, doing what stars do in the dark. A star is born slowly, in cold and silence, from the simplest materials there are. The collapse of a molecular cloud is not simply a matter of gravity winning against pressure. Magnetic fields thread through the cloud like invisible wires, and they resist the collapse. Field lines that run through a region of gas must be compressed along with the gas, and the increased field strength pushes back against the compression. The process by which stars form despite this magnetic support is called ambipolar diffusion. The gas contains a small fraction of ions that are coupled to the magnetic field, while the neutral molecules that make up most of the cloud are not. Over millions of years, the neutral material slowly drifts through the ions and the magnetic field, allowing the density to build up in the core of a cloud fragment even as the magnetic field gradually leaks outward. It is a slow seeping through a magnetic barrier, patient and gradual as geological erosion. The disk of gas and dust that forms around a protostar is not a passive structure. It is actively turbulent, threaded with its own magnetic fields, and the site of complex chemistry. Molecules form on the surfaces of dust grains in the cold outer regions of the disk: water ice, carbon monoxide, complex organic compounds including alcohols and amino acid precursors. When astronomers examine the spectra of the gas around young stellar objects, they find an extraordinary chemical complexity, the raw materials of biology drifting in the frigid outer disk of a star still negotiating its way to ignition. The disk is also the birthplace of planets, their solid cores growing from the slow sticking together of dust grains, aggregating over millions of years into pebbles, then boulders, then protoplanets, then worlds. The bipolar jets that young stars produce leave visible marks on the surrounding nebula. When a jet of material moving at several hundred kilometers per second plows into the slower-moving gas of the surrounding cloud, the collision produces a bright knot of shocked gas called a Herbig-Haro object, named for the American and Mexican astronomers who first catalogued them in the 1940s and 1950s. These objects glow with the emission lines of shocked hydrogen and other molecules, marking the point of impact like a bow wave. They move visibly even over human timescales. Astronomers who rephotograph a Herbig-Haro object after a decade or two can see it has shifted position, advancing into the surrounding cloud at a speed that, knowing the distance, can be directly measured. They are the most visible evidence that the process of star formation, so often described in geological units of time, is also happening on scales the human mind can follow. For the Sun, the record of its formation is preserved partly in the composition and structure of our own solar system. The planets, their moons, the asteroids, the comets, all formed from the same disk that the protosolar cloud produced, and their compositions reflect the chemistry of the disk 4.5 billion years ago. The oldest solid material in the solar system, certain types of meteorite, called carbonaceous chondrites, that contain tiny granules called calcium-aluminium-rich inclusions, dates to approximately 4.567 billion years, providing the most precise timestamp for the formation of the solar disk. The Sun itself formed slightly earlier, its gravitational collapse beginning perhaps 500,000 years before the disk solidified into its first solid grains. Every atom in your body was in that cloud. Perhaps the most remarkable implication of what we know about star formation is how universal it is. The same process, gravitational collapse, fragmentation, disk formation, ignition, has been repeating throughout the universe since the first stars formed roughly 180 million years after the Big Bang. The first stars were made of almost pure hydrogen and helium. There were no heavier elements yet, because no stars had yet lived and died to produce them. They were enormous, perhaps hundreds of times the mass of the Sun, and they burned brilliantly and briefly, seeding the universe with the first carbon and oxygen and iron when they died. Every subsequent generation of stars formed from material enriched by those that came before, incorporating carbon, oxygen, silicon, and iron from the deaths of earlier stars. The Sun is a third-generation star, at minimum. A star is born slowly, in cold and silence, from the simplest materials there are. Rest now, in the knowledge of that quiet beginning. Chapter 2: Nuclear Fusion. At the center of the Sun, right now, something is happening that has no equivalent anywhere on the surface of the Earth or in any technology that human beings have yet managed to build and sustain. In a region roughly the size of Jupiter, under a pressure of 250 billion times the atmospheric pressure at sea level and a temperature of approximately 15 million degrees Kelvin, hydrogen nuclei, are bare protons, stripped of their electrons by the intensity of the heat, are colliding with each other so rapidly and so violently that something which is classically forbidden becomes possible. Two protons fuse. And in that fusion, a small quantity of matter is converted directly into energy. According to the most famous equation in the history of science, energy equals mass multiplied by the square of the speed of light. The Sun is doing this 600 million tons at a time, every second, and it has been doing it for 4.5 billion years. The reaction that powers the Sun is called the proton-proton chain, and it unfolds in 3 steps of remarkable delicacy. In the first step, 2 protons collide and fuse to form a deuterium nucleus, a nucleus containing 1 proton and 1 neutron. For this to happen, one of the protons must transform into a neutron, a process that involves the weak nuclear force and the simultaneous emission of a positron and a neutrino. This first step is extraordinarily rare. Any given proton in the Sun's core waits, on average, approximately 10 billion years before it encounters exactly the right conditions to fuse. The entire energy output of the Sun is sustained by a process in which individual reactions are almost vanishingly improbable. It is the sheer number of protons in the core, a number that makes the total count of grains of sand on Earth seem modest, that produces the steady, reliable energy output we observe. In the second step of the chain, the deuterium nucleus captures another proton to form helium-3, a nucleus with 2 protons and 1 neutron. This step is considerably faster than the first. In the third step, 2 helium-3 nuclei collide and merge, then immediately eject 2 protons, leaving behind a single helium-4 nucleus, 2 protons and 2 neutrons, the ordinary helium found in balloons and in the atmospheres of planets. The net result of the entire chain is that 4 hydrogen nuclei have been converted into 1 helium nucleus, 2 positrons, 2 neutrinos, and a substantial quantity of energy in the form of gamma radiation. The helium nucleus is slightly less massive than the 4 protons that went into making it, and that missing mass, approximately 0.7% of the original, has been released as energy. 0.7% sounds like very little. But when you multiply it by the speed of light squared, a number equal to roughly 90 quadrillion meters squared per second squared, and then multiply by the mass of material being processed, the result is staggering. Every second, the Sun converts roughly 4 million tons of matter directly into energy. For million tons, the mass of a small mountain vanishes from physical existence and becomes light and heat, every second, without pause. Over the 4.5 billion years of the Sun's life so far, the total mass lost to fusion is approximately 100 times the current mass of the Earth. The Sun is smaller, very slightly, than it was when it formed. It is burning, in the most literal sense of mass becoming energy. The gamma-ray photons produced in the core do not travel directly outward to the surface. They cannot. The interior of the Sun is so dense, even denser than lead, though it is composed of gas rather than solid material, that a photon travels only a fraction of a centimeter before it is absorbed by a nucleus and re-emitted in a random direction. The journey from the core to the surface of the Sun is therefore not a straight line but a random walk, a path of billions upon billions of short steps, each in an arbitrary direction, gradually and inefficiently diffusing outward. By some estimates, the time required for energy produced in the core to reach the surface of the Sun, taking this tortuous, wandering path, is between 10,000 and 100,000 years. The sunlight warming the Earth on any given summer afternoon was born in a nuclear reaction that occurred long before the pyramids were built, perhaps before humanity existed in its modern form. We are bathed, every day, in ancient fire. There is a particle produced in the fusion reaction that does not behave this way. The neutrino, a nearly massless, chargeless particle produced in the first step of the proton-proton chain, interacts with matter so weakly that the entire Sun is essentially transparent to it. A neutrino produced in the solar core passes through the entire body of the Sun in approximately 2 seconds, and through the Earth without noticing it. Right now, at this moment, a stream of approximately 65 billion solar neutrinos is passing through every square centimeter of the Earth's surface every second. Through the roof above you. Through the mattress beneath you. Through your body. Through the floor. Into the planet. Out the other side. Into the void. They carry energy, a small fraction of the total, but they carry it away so completely that it is lost to the Sun forever. The detection of solar neutrinos is one of the most technically demanding achievements in modern physics. neutrino detectors are enormous tanks of ultra-pure water or other substances, buried deep underground to shield them from the cosmic rays that would otherwise produce false signals, in which the occasional neutrino interaction produces a tiny flash of light detectable by surrounding photomultiplier tubes. The Superkamio Kande detector in Japan, a cylinder 41 meters in diameter and 41 meters tall, filled with 50,000 tons of ultra-pure water and lined with 11,000 photomultiplier tubes, detects roughly 15 solar neutrinos per day. The rest, tens of trillions per second, pass through entirely undetected and continue on their way. In more massive stars, those 3 or more times the mass of the Sun, the core temperatures are high enough to drive a different fusion pathway, known as the CNO cycle, in which carbon, nitrogen, and oxygen nuclei act as catalysts to convert hydrogen into helium more rapidly. The CNO cycle produces the same end product as the proton-proton chain, but it proceeds much more quickly, which is why massive stars are far more luminous than the Sun despite having cores that are not proportionally larger. A star of 20 solar masses may shine with a luminosity 100,000 times greater than the Sun's, burning through its hydrogen fuel at a correspondingly furious rate. The Sun's hydrogen fuel is sufficient, at its current rate of consumption, for approximately another 5 billion years. By cosmological standards, this means the Sun is approximately middle-aged. It has lived roughly as long as it has left to live. This will not feel urgent from any human perspective. The Sun rises tomorrow as reliably as it rose today, and as reliably as it has risen every day since the Earth formed, and will continue to do so for a span of time that simply exceeds any ordinary conception of the future. The fire in the Sun is patient, and it is vast, and it burns in its own time. The rate of fusion in the Sun is often misunderstood as violent or explosive, associated, perhaps, with the hydrogen bomb, which also operates on nuclear fusion. But the comparison is misleading. A hydrogen bomb achieves fusion by creating the conditions for it in an uncontrolled, instantaneous release. The Sun's fusion is so slow and so controlled by comparison that any given cubic meter of the solar core produces only a few hundred watts, roughly the heat output of a warm radiator. The Sun produces so much energy in total only because it is so enormously large, with so many cubic meters of fusing core. If you could bring a piece of the Sun's core to Earth, a cubic meter of it would feel merely warm. The Sun is not a bomb. It is an extraordinarily patient, enormously slow, impossibly vast nuclear furnace. The detection of solar neutrinos is one of the great triumphs of 20th century physics, and one of its most dramatic puzzles. In the 1960s, the American chemist Raymond Davis Jr. built a neutrino detector in a gold mine in South Dakota, a tank holding 380,000 liters of dry cleaning fluid, designed to capture the rare interaction of a solar neutrino with a chlorine atom. The detector should have captured roughly 1 neutrino per day, based on theoretical predictions. It captured only 1/3 of that. For decades, this deficit, the solar neutrino problem, was a source of significant tension between solar physics and particle physics. The resolution, finally confirmed in the early 2000s, was that neutrinos oscillate between 3 flavors as they travel, and Davis's detector was sensitive to only 1 flavor. The missing neutrinos were not absent, they had simply changed into types his detector could not see. Aeolseismology is the study of sound waves in the Sun, pressure waves that propagate through the solar interior and create subtle oscillations of the solar surface detectable from Earth. By analyzing these oscillations, which repeat with periods of approximately 5 minutes, solar physicists have been able to map the interior structure of the Sun with extraordinary precision, in the same way that geologists use seismic waves to map the interior of the Earth. Aeolseismology has confirmed the theoretical models of the solar interior to a high degree of accuracy, revealing the depth of the convection zone, the rotation rate of the interior at different depths, and the helium abundance of the solar core. The Sun, examined in this way, becomes transparent, not to light, but to sound. The question of why the early Earth was not frozen is one of the more interesting puzzles in planetary science. Astrophysical theory predicts that the Sun, when it was young, shone with only about 70% of its current luminosity, the faint young sun problem, identified by the astronomers Carl Sagan and George Mullen in the early 1970s. At that luminosity, simple models predict that the Earth's oceans should have been frozen solid. But the geological record clearly shows liquid water on Earth at least 4.4 billion years ago, within a few 100 million years of the planet's formation. The resolution likely involves a much higher concentration of greenhouse gases in the early atmosphere, carbon dioxide and methane, that compensated for the reduced solar output. As the Sun has brightened, the atmosphere has changed, and the Earth has remained, more or less, at habitable temperatures. The end of the Sun's hydrogen-burning phase will be determined by the state of its innermost core. As helium accumulates in the core, the central region where fusion occurs gradually shrinks. The helium, not yet hot enough to fuse, simply sits inertly, compressing the surrounding hydrogen-burning region into a narrower shell. The Sun brightens slightly over its main sequence lifetime as a result of this process. It is currently about 30% more luminous than it was when it formed, and will be perhaps 40% more luminous by the time it finally departs the main sequence. The brightening is slow, on timescales of billions of years, and no single generation of any organism on any planet could perceive it. But it is happening, continuously, as the core composition evolves. The fire in the Sun is patient, and it is vast, and it burns in its own time. Let it burn while you sleep. Chapter 3 of the Light. A photon is born in the core of the Sun, and its first journey is nowhere. It travels an immeasurably small distance, a fraction of a centimeter, perhaps less, before it is absorbed by a nucleus of gas and disappears. Then it is remitted, in a completely random direction, and travels another fraction of a centimeter before being absorbed again. And then again. And then again. This process of absorption and re-emission, of being born and destroyed and reborn in a new direction, repeats billions upon billions of times as the energy of the original nuclear reaction begins its slow migration outward from the core toward the surface of the Sun. The photon, if you can call it the same photon across all these absorptions and re-emissions, is performing what mathematicians call a random walk, a path that drifts, on average, outward, but that doubles back on itself, wanders sideways, reverses, loops, and meanders through the dense solar interior with the aimlessness of a particle that has no sense of direction and no memory of where it has been. The time required for this random walk to carry energy from the solar core to the surface is one of the more surprising facts in astrophysics. Different methods of calculation yield somewhat different numbers, but the best estimates suggest that the journey takes somewhere between 10,000 and 100,000 years. In that span of time, on the surface of the Earth, the most recent ice age has begun and ended. Human civilizations have risen and collapsed. Languages have been born, flourished, and gone silent. And yet the energy released in a particular nuclear reaction in the solar core has spent all that time diffusing, photon by photon, absorption by absorption, through approximately 700,000 kilometers of gas before reaching the layer of the Sun where it can finally escape. That layer is called the photosphere. It is the surface of the Sun, not a hard surface in any physical sense, since the Sun is entirely gaseous, but the layer at which the solar gas transitions from being opaque to being transparent. Below the photosphere, a photon travels only a very short distance before being absorbed. Above the photosphere, the gas is thin enough that a photon can travel freely, in a straight line, through space. When a photon reaches the photosphere after its century-spanning random walk through the solar interior, it is released. And from that moment, everything changes. The photon, traveling at 300,000 kilometers per second, crosses the 93 million miles from the Sun to the Earth in approximately 8 minutes and 20 seconds. 8 minutes. To cover the same distance that took it 10,000 years to travel within the Sun. Those 8 minutes are a kind of freedom, the first straight line travel the photon has made since it was created. It moves through the vacuum of space, which offers nothing to absorb it, nothing to deflect it, nothing to interfere with its trajectory in any way. It arrives at the upper atmosphere of the Earth, begins its final short journey through 100 kilometers of air, and depending on the time of day, the cloud cover, and the position of the sky it is aimed at, it either reaches the ground and is absorbed, warming the soil or the skin, or it is scattered back into space, giving the sky its blue color. But the sun is not the only source of light in the night sky. Look upward, past the atmosphere, past the solar system entirely, and the light arriving at this planet is ancient in ways that make the sun's 8-minute photons seem almost immediate. The star Proxima Centauri, the nearest stellar neighbor beyond our sun, is 4.24 light-years away, a distance that light, traveling at its maximum speed, takes 4 years and 3 months to cross. The light arriving from Proxima tonight began its journey in the early part of whatever year falls 4 years and 3 months before this moment. The events of those years, whatever happened in the world, whatever changed in your life, were unfolding at the same time as that light was in transit, covering the void between two stars in silence and darkness, arriving now, here, at this moment. The light from Sirius, the brightest star in the night sky after the sun, takes about 8.5 years to reach us. Aldebaran, the brilliant orange star that forms the eye of Taurus the bull, is 65 light-years away. Rigel, the blue-white star at the lower right of Orion, is approximately 860 light-years distant. When the light now arriving from Rigel began its journey, the Italian poet Dante Alighieri was composing the Divine Comedy. The medieval world, with its cathedrals and its plagues and its wandering scholars and its entire conception of the universe, existed under the same sky we now live under, while that light was traveling toward us, in the dark, in no particular hurry, at the speed of light. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, visible as a faint smear of light on clear dark nights in the constellation Andromeda, is 2.5 million light-years away. The light arriving from Andromeda tonight began its journey 2.5 million years ago, when the ancestors of Homo sapiens were making simple stone tools in the grasslands of East Africa, when the ice ages were just beginning to intensify, when the climate of Earth was substantially different from what it is today and the continents looked very nearly as they do now, but the surface of the Earth was populated by animals we would barely recognize. That light has spent 2.5 million years traveling to reach your planet, and it arrives here every night, falling on every surface that faces the right part of the sky, in quantities so small that an ordinary human eye can just barely detect the galaxy as a slightly brighter patch of darkness. This is what looking at the sky means. Every point of light you see, from the faintest star to the brightest, is a message from the past, from a source as it existed years or centuries or millions of years ago, not as it exists now. Some of the stars you can see with the naked eye no longer exist. They have died in the interval between the departure of their light and its arrival at your eye, and you do not yet know this because the news of their death is still in transit, still crossing the dark between them and you, and will not arrive for centuries or millennia. The sky is a record of the past, not a window on the present. Looking upward is, always and inescapably, a form of looking backward in time. There is something strangely calming about this, if you allow yourself to sit with it. The light that fills the night sky is old. It has been traveling through the void for longer than most human civilizations have existed, and in most cases longer than human civilization itself has existed. It arrives quietly, at the speed of light, carrying information about the temperature and composition and motion of its source, falling on the surfaces of this world with complete indifference to what it finds there. It warmed the oceans of the Cretaceous. It fell on the ice of the last glacial maximum. It illuminated the faces of every person who has ever looked up on a clear night and wondered what was out there. And now it falls on you, or on the roof above you, or on whatever surface faces the sky at this moment. The light that travels from a star to your eye does not always arrive unaltered. The interstellar medium, the gas and dust between the stars, is not perfectly transparent. Dust grains scatter and absorb short wavelengths of light more than long wavelengths, so that starlight traveling long distances through dusty regions emerges redder than it began, its blue end attenuated, its red end relatively unaffected. This interstellar reddening is distinct from the Doppler redshift of recession, and astronomers must account for it carefully when interpreting stellar spectra. Dense molecular clouds are so thoroughly opaque that they appear as dark patches against the stellar background, not voids in the star field but thick curtains of dust through which no optical light passes. What is hidden behind them can be seen only in radio waves or infrared, which penetrate the dust far more easily. Beyond the visible spectrum, the universe emits radiation at wavelengths no human eye can detect. Stars like Betelgeuse shine most brilliantly in the infrared, their cool red surfaces radiating energy that passes through Earth's atmosphere and can be detected by infrared telescopes. Hot young stars and supernova remnants glow fiercely in ultraviolet and X-ray. Pulsars sweep the sky with radio beams. The entire universe is bathed in a faint, uniform microwave radiation, the cosmic microwave background, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, that is the cooled remnant of the light released 380,000 years after the Big Bang, when the universe first became transparent. This is the oldest light in the universe, an image of the infant cosmos imprinted on the sky in every direction. The photons of the microwave background have been traveling for 13.8 billion years. One of the most extraordinary ways that light reveals the universe involves not speed but curvature. Massive objects, galaxies, galaxy clusters, even individual stars, curve the space through which light travels, deflecting photons from their straight-line paths. This gravitational lensing, predicted by Einstein's general relativity and first confirmed during the solar eclipse of 1919, can produce spectacular effects. A galaxy directly behind a massive foreground cluster may be stretched into a circle of light, an Einstein ring, or multiplied into several separate images arranged around the lensing mass. For astronomers, gravitational lensing is both a nuisance, distorting the apparent positions and shapes of distant objects, and an extraordinary tool, magnifying light from galaxies so remote and so dim that they could not otherwise be seen at all. The sensitivity of the human eye to light is, in its own right, a remarkable thing to consider. Under dark-adapted conditions, the eye can detect as few as 5 to 10 photons arriving at the retina, a quantity of light so small that it represents the output of a candle at a distance of about 27 kilometers. The stars visible to the naked eye are delivering photons to the eye at rates ranging from a few thousand per second, for the very brightest, to fewer than 100 per second for stars at the edge of naked eye visibility. The faintest star you can see on a clear dark night is delivering perhaps 50 photons per second to each of your eyes. 50 ancient photons per second, from a source hundreds of light-years away, is enough for the human eye to register a star. The light is patient. It has come a very long way. It can wait while you sleep. Chapter 4: The Surface. The surface of the Sun is not a surface in any sense that the word suggests to a human mind. It is not solid. It is not still. It is not even particularly well-defined. It is the place where a ball of gas 109 times the diameter of Earth transitions from being dense enough to be opaque to being thin enough to be transparent, and this transition happens over a zone of perhaps a few hundred kilometers, vast by human standards, but razor-thin relative to the size of the Sun itself. Stand at this notional surface, the photosphere, and the view would be something entirely unlike anything in ordinary experience, a boiling, seething, constantly rearranging landscape of gas, bright enough to blind in an instant, hot enough to vaporize any material in existence, patterned with structures that look almost familiar, almost like the surface of water, and yet exist at a scale that makes the Earth look like a small stone dropped in an ocean. The most immediately striking feature of the photosphere, visible even through a modest solar telescope fitted with the appropriate filters, is its granular texture. The entire visible surface of the Sun is covered with granules, bright, roughly polygonal regions, each typically between 1,000 and 2,000 kilometers across, separated by darker, slightly cooler boundaries. Each granule is the top of a convection cell, a column of hot gas rising from below the photosphere, spreading outward across the surface, cooling as it radiates its energy into space, and then sinking back down in the darker lanes at the edges. A single granule rises, spreads, and sinks in approximately 8 to 10 minutes. The entire photosphere is tiled with perhaps 1 million of these cells at any moment, rising and sinking in a constant rhythm, the surface of the Sun breathing in and out in a pattern that looks, from far enough away, almost as if the star is alive. Above the granules, and over timescales of days rather than minutes, larger convection patterns called supergranules organize the surface into still larger cells, each roughly 30,000 kilometers across. And at still larger scales, the Sun's differential rotation, the fact that the equator rotates faster than the poles, stretches and twists the magnetic field lines threading through the solar interior, eventually causing them to break through the surface in tangled loops and arches. Where the magnetic field is strongest, it suppresses the upward flow of hot gas from below. The suppressed regions are cooler than their surroundings, still thousands of degrees, but cooler, and they appear darker by contrast. These are sunspots, and they have been observed by astronomers since Galileo first turned his telescope toward the Sun in 1610, noting their positions and watching them drift across the solar disk as the Sun rotated beneath them. Sunspots are far from small. A large sunspot can easily exceed the diameter of the Earth. The largest sunspot group ever recorded, in 1947, covered an area estimated at approximately 6,000 million square kilometers, more than 10 times the surface area of Earth. Sunspots tend to occur in pairs or groups, their magnetic polarities arranged in a pattern that reflects the underlying structure of the Sun's magnetic field. They form, grow, split, merge, and decay over periods of days to months, with the number present at any given time rising and falling in a cycle of approximately 11 years that reflects the changing intensity of the Sun's magnetic activity. At the peak of the solar cycle, when sunspot numbers are highest, the Sun is also most active in other ways. Solar flares, sudden explosive releases of energy in the Sun's atmosphere above active regions, powered by the reconnect ion and annihilation of twisted magnetic field lines, can release energy equivalent to billions of hydrogen bombs in a matter of minutes. These flares emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays, and they can cause temporary disturbances to radio communications and satellite systems on Earth when the radiation arrives 8 minutes later. Coronal mass ejections, enormous clouds of plasma and magnetic field hurled outward from the Sun by the explosive release of magnetic energy, travel through the solar system at speeds of up to a few thousand kilometers per second, taking anywhere from a few hours to a few days to reach Earth. When a large coronal mass ejection is aimed at Earth, it can trigger geomagnetic storms that produce brilliant auroras visible at unusually low latitudes, while also potentially causing disruptions to power grids and satellites. Beyond the photosphere lies a thin, reddish layer called the chromosphere, visible during total solar eclipses as a brief ring of pinkish light around the Moon's disk, and above that, the corona, the Sun's outermost atmosphere, extending millions of kilometers into space and forming the pale, white, pearly light that surrounds the Moon during a total eclipse. The corona is one of the great unsolved problems of solar physics. It is, by every intuitive expectation, far hotter than it ought to be. The photosphere has a temperature of approximately 5,500 degrees Celsius. The corona, however, has a temperature of 1 to 3 million degrees, several hundred times hotter than the surface below it. This is deeply counterintuitive. If you move a thermometer away from a fire, the reading decreases, not increases. Something in the corona is adding energy, heating it to extraordinary temperatures far from the source of nuclear energy in the core. The leading candidates involve the dissipation of magnetic waves propagating outward from the photosphere, and the explosive nanoflares produced by the constant small-scale reconnection of magnetic field lines. The precise mechanism remains a subject of active research and some debate. From the corona, a constant wind of charged particles, electrons, protons, and heavier ions, streams outward through the solar system in all directions. This solar wind travels at between 400 and 800 kilometers per second, reaching the orbit of Earth in roughly 3 to 4 days and extending far beyond the outermost planets, eventually thinning to the point where it merges with the interstellar medium at a boundary called the heliopause. When the solar wind encounters the Earth's magnetic field, it compresses the field on the sun-facing side and stretches it into a long tail on the other. The interaction between the wind and the field channels particles toward the polar regions, where they enter the atmosphere and excite the gases there, producing the auroras, the northern and southern lights, that curtain the high-latitude skies in green and red and violet on magnetically active nights. None of this is still. None of it is quiet. The surface of the sun is a place of constant, violent, beautiful activity, convecting and erupting and radiating and blowing its outermost atmosphere into space in a wind that reaches every planet. It has been like this for 4.5 billion years. It will be like this for approximately 5 billion more. And it is happening right now, far above the roof of this room, in the bright side of the world, in the daylight you are not in. The most powerful geomagnetic storm ever recorded struck the Earth on the 1st and 2nd of September, 1859, an event known as the Carrington Event, named for the British astronomer Richard Carrington, who observed the associated solar flare directly through his telescope in white light and immediately recognized it as something extraordinary. The coronal mass ejection produced by the flare reached Earth in approximately 18 hours, far faster than typical, because it was preceded by an earlier smaller ejection that had cleared a path through the solar wind. When it struck Earth's magnetic field, the resulting geomagnetic storm was of extraordinary intensity. Auroras were visible at latitudes as low as Cuba and Hawaii. Telegraph lines caught fire. Telegraph operators received electric shocks. Some telegraph stations reported being able to send messages even after disconnecting their batteries, powered entirely by the induced currents from the geomagnetic disturbance. An event of similar intensity today, with the global infrastructure of electrical grids and satellite communications and internet cables, would be catastrophic by any measure. The aurora itself, the northern or southern lights produced by charged particles guided into the polar atmosphere by the Earth's magnetic field, is one of the most beautiful consequences of the solar-terrestrial relationship. The colors of the aurora are produced by the emission of light from atmospheric gases excited by the incoming energetic particles. Oxygen at altitudes of around 100 kilometers emits the most common color, a vivid green. At higher altitudes, above 200 kilometers, oxygen emits red instead. Nitrogen produces blue and purple. A full-spectrum aurora on an active night may display all of these simultaneously, green curtains rippling slowly across the sky, with red above and occasional blue-purple lower down, shifting and folding in patterns that have no equivalent in ordinary terrestrial experience. Watching an aurora is, subjectively, unlike watching any other natural phenomenon. Space telescopes, particularly those operating in the ultraviolet and X-ray, have transformed our view of the solar surface and atmosphere. The Solar Dynamics Observatory, launched by NASA in 2010, observes the Sun in 10 different wavelengths of extreme ultraviolet and produces images of extraordinary detail every 12 seconds, continuously. In these wavelengths, the Sun is a churning, intricately structured object very different from the smooth, featureless disk it appears to the unfiltered naked eye. Loops of magnetic field, traced by hot plasma, arch above active regions. Prominent clouds of cooler gas hang suspended in the corona. Coronal holes, dark regions where the magnetic field opens outward into space, allowing the solar wind to flow freely, appear as dark patches on the UV disk. The solar atmosphere, invisible in ordinary light, is in these wavelengths a place of great complexity and beauty. The Parker Solar Probe, launched in 2018, is the closest approach to the Sun that any human-made object has ever achieved. Its orbit brings it within approximately 8 million kilometers of the solar surface, close enough that the probe's carbon composite heat shield faces temperatures exceeding 1,400 degrees Celsius. It has made the first in-situ measurement of the solar wind within the corona itself, sampling the material of the solar atmosphere directly rather than inferring its properties from remote observations. It has measured magnetic switchbacks, rapid reversals of the solar wind's magnetic field that occur at frequencies suggesting the corona is threaded with far more fine-scale structure than previously imagined. The probe approaches the Sun in relative silence, instruments running, collecting data on the most intimate observations of a star that any instrument has ever made. The Sun is never at rest. But you can be. Chapter 5: The Stellar Spectrum. When sunlight passes through a glass prism, it spreads into the familiar rainbow of colors, red at one end, violet at the other, with orange and yellow and green and blue between them, the visible spectrum laid out in its full width. This is because the prism bends different wavelengths of light by different amounts, separating what white light contains into its components. The rainbow that results is beautiful, and most people leave it there. But a closer examination of that rainbow reveals something more, a series of dark lines, narrow gaps in the spectrum where specific wavelengths of light are entirely absent. These lines, first described systematically in the early 19th century by the German physicist Joseph von Fraunhofer, who mapped hundreds of them and assigned them letters for reference, are among the most important features in all of science. They are the fingerprints of the atoms in the solar atmosphere. Each element, when heated to a gas, absorbs light at a specific set of wavelengths determined by the quantum structure of its electrons. Sodium absorbs at two closely spaced wavelengths in the yellow. Hydrogen absorbs at a series of wavelengths spread across the spectrum. The Balmer series, named for Johann Balmer, includes the vivid red line of hydrogen alpha and extends through green and blue-violet. Calcium, iron, magnesium, and dozens of other elements each produce their own characteristic patterns of absorption lines, as distinctive and unambiguous as a barcode. When sunlight passes through the cooler gases of the solar atmosphere on its way outward, those gases absorb the wavelengths they are sensitive to, leaving the characteristic dark lines in the spectrum. The implication of this is remarkable. By examining the spectrum of a star, astronomers can determine its chemical composition with extraordinary precision, from a distance of thousands of light-years, without any physical contact with the star or any material from it. This is not an approximation or an inference, it is a direct read of the atomic absorption properties of the gases in the stellar atmosphere, as precise as any laboratory measurement. The dark lines in the spectrum of Sirius or Vega or Betelgeuse are as informative as a sample brought back in a spacecraft. They tell us what the star is made of, in what proportions, and at what temperature those materials are found. Temperature, it turns out, determines which absorption lines are most prominent in a stellar spectrum, because temperature determines which electrons are in which energy states in which atoms, and only electrons in specific states will absorb specific wavelengths. The hottest stars, with surface temperatures above 25,000 Kelvin, show spectra dominated by ionized helium and multiply ionized oxygen and nitrogen. Stars in the intermediate temperature range, between 7,500 and 10,000 Kelvin, show the strongest hydrogen absorption lines, because at those temperatures the hydrogen electrons are in precisely the right energy state to absorb visible light. Cooler stars, with surface temperatures below 5,000 Kelvin, show spectra in which the absorption lines of metals and even molecular compounds become prominent, because the lower temperatures allow these structures to persist in the atmosphere. This temperature sequence of stellar spectra was classified systematically in the late 19th and early 20th centuries at the Harvard College Observatory, in a project that employed a team of women, given the title computers, to examine and classify the spectra of hundreds of thousands of stars from photographic plates. The scheme eventually adopted was largely the work of Annie Jump Cannon, who classified more than 350,000 stellar spectra over her career with a speed and accuracy that her contemporaries found astonishing. The sequence she established, designated by the letters O, B, A, F, G, K, M, ordered from hottest to coolest, is still in use today, often remembered by the mnemonic "Oh be a fine girl, kiss me." Our Sun is a G-type star, a middle-temperature, middle-luminosity star of unremarkable properties by the standards of the galaxy, and yet the star on which all of Earth's life depends. The spectrum reveals not only composition and temperature but motion. When a light source moves toward or away from an observer, the wavelengths of the light it emits are compressed or stretched in proportion to the speed of approach or recession, an effect analogous to the changing pitch of a passing siren, and described by the same mathematics. This is the Doppler effect, and in stellar spectra it manifests as a systematic shift of all the absorption lines toward shorter wavelengths, the blue end of the spectrum, if the star is approaching, or toward longer wavelengths, the red end, if the star is receding. The shift is small but measurable, and it allows astronomers to determine the radial velocity of a star, how fast it is moving toward or away from Earth, with great precision. By tracking these shifts over time, it is possible to detect the gravitational wobble induced in a star by an orbiting planet that is far too small and dim to see directly. This technique, radial velocity measurement, was used to discover the first planets orbiting other stars, in the 1990s, and it has since identified hundreds. The Hertzsprung-Russell diagram, devised independently by the Danish astronomer Ejnar Hertzsprung and the American Henry Norris Russell in the early 20th century, plots the luminosity of stars against their spectral type, and reveals a striking pattern. Rather than being scattered randomly across the diagram, stars cluster in distinct regions. The main sequence, a broad diagonal band running from upper left, where the hot, luminous, blue stars are found, to lower right, where the cool, dim, red stars cluster, contains approximately 90% of all stars, including the Sun. A star occupies the main sequence as long as it is burning hydrogen in its core. Its position on the sequence is determined almost entirely by its mass. Above and to the right of the main sequence lies a scattering of giant and supergiant stars, cool but luminous, large in radius. Below the main sequence lies a small population of white dwarfs, hot but dim, compact remnants of dead stars. The diagram is a kind of map of stellar lives. The position of a star on the diagram tells you what it is doing, roughly how old it is relative to its lifespan, and where it is headed. The Sun, sitting comfortably in the middle of the main sequence, has approximately 5 billion years left before it departs and becomes something very different. The blue supergiants in the upper left have perhaps a few million years remaining. They burn furiously and die young, by stellar standards, their brief bright lives the most spectacular in the galaxy. The spectrum of a single star, examined with sufficient care, contains an entire biography. Not metaphorically, literally. The wavelengths of its absorption lines name its elements. The temperature class names its color and its stage of life. The Doppler shift of those lines names its motion through space. The breadth and shape of the lines, examined closely enough, can reveal the star's surface gravity, its rotation rate, and the strength of its magnetic field. All of this information is carried in light that has traveled years or centuries to reach a telescope on the ground. The universe, if you know how to read it, writes everything down. One of the most celebrated stories in the history of spectroscopy involves an element that was discovered in the Sun before it was found on Earth. In 1868, the French astronomer Pierre Janssen and the British astronomer Norman Lockyer independently observed a spectral line in the Sun during a solar eclipse, a yellow line that did not correspond to any known element. Lockyer proposed that it was the signature of an undiscovered element and named it helium, after Helios, the Greek personification of the Sun. It was not until 1895 that William Ramsay isolated helium from a uranium mineral on Earth and confirmed that the extraterrestrial element was indeed present on our own planet. an element discovered in a star, at a distance of 93 million miles, through nothing more than the examination of light, and named for that star, before it was ever found in a sample anyone could hold in their hands. The same technique that reads the chemistry of stars has also been applied to the atmospheres of planets orbiting other stars. When a planet transits its host star, passing in front of it as seen from Earth, a tiny fraction of the star's light filters through the planet's atmosphere before reaching our telescopes, and the absorption lines produced by atmospheric gases imprint themselves on the stellar spectrum. This technique, transmission spectroscopy, has already detected water vapor, methane, carbon dioxide, and sodium in the atmospheres of certain exoplanets. The James Webb Space Telescope, launched in December 2021, is designed in part to carry out this kind of atmospheric characterization with a sensitivity far beyond what was previously possible, and early results have confirmed the detection of carbon dioxide in the atmosphere of a giant exoplanet, the first clear detection of an individual atmospheric molecule in a world orbiting another star. The most distant light that spectroscopy has examined comes from quasars, the intensely luminous cores of distant galaxies, powered by supermassive black holes accreting mass at enormous rates and glowing with the light of trillions of suns. Quasar spectra reveal, through the Doppler shift of their emission lines, that the most distant quasars are receding from us at speeds approaching the speed of light, their redshift so extreme that ultraviolet emission lines are shifted entirely out of the ultraviolet and into the visible or even the infrared. These redshifts tell us how far away the quasars are, and therefore how far back in time we are looking. The most distant quasars observed lie more than 13 billion light-years away. We are seeing them as they were when the universe was less than 1 billion years old, before most galaxies had formed, before most of the stars in the present-day universe had ignited. The spectrum of our own planet, seen from space, is itself an interesting object of study. If an alien civilization were to examine the Earth's spectrum from a distant star system, what would they find? Water vapor and carbon dioxide, certainly, common in planetary atmospheres. But also oxygen in extraordinary quantities, 21% of the atmosphere, far more than could be explained by any geological process. And ozone, produced by the photochemistry of oxygen in the stratosphere. And methane, which reacts with oxygen and is therefore thermodynamically unstable. Its presence alongside oxygen would indicate that something is continuously producing it. The Earth spectrum, analyzed by a sufficiently sophisticated civilization, would be a clear signal of biological activity, a chemical imbalance maintained by life, visible across light-years, encoded in the light reflected from a small blue planet. The stars are telling their own stories, in light, every moment of every night. You can rest while they tell them. Chapter 6: Variable Stars. Not all stars shine steadily. The vast majority of the points of light you see on a clear night appear constant, the same brightness, night after night, century after century, but this constancy is partly an artifact of human timescales. Observe a star carefully enough, for long enough, and many of them reveal themselves to be variable, changing in brightness in patterns that range from the rapid and mathematically precise to the slow and barely perceptible, for reasons ranging from the physical oscillation of the star itself to the geometric accident of a companion passing in front of it. Variable stars are not curiosities at the margin of stellar astronomy. They are, in several important ways, the instruments through which astronomers have measured the universe. The most cosmologically significant class of variable stars is the Cepheid variables, a group of pulsating stars whose brightness rises and falls with extraordinary regularity, like a slow, cosmic heartbeat. A Cepheid variable brightens and dims because the star is literally expanding and contracting. The outer layers of the star pulsate inward and outward, driven by a mechanism involving the ionization of helium in a layer beneath the stellar surface. When the helium is singly ionized, it is partially opaque and traps radiation, building pressure that pushes the outer layers outward. As the layer expands and cools, the helium becomes doubly ionized and suddenly more transparent, the pressure drops, and the layers fall back inward under gravity. The cycle then begins again. The period of this pulsation, the time from one maximum brightness to the next, can range from a few days to a few months, depending on the luminosity of the star. The critical discovery, made by the American astronomer Henrietta Swan Leavitt in 1908, was that the period of a Cepheid variable is directly related to its intrinsic luminosity, the actual amount of energy it emits. Leavitt was studying Cepheid variables in the Small Magellanic Cloud, a satellite galaxy of the Milky Way, whose stars are all at approximately the same distance from Earth. She found that the brighter the Cepheid, the longer its period of variation, a relationship so clean and precise that it could be described by a simple mathematical equation. The implication was immediately obvious to astronomers. If you measure the period of any Cepheid variable anywhere in the sky, you can calculate its intrinsic luminosity, compare it to its observed brightness, and determine how far away it is. The Cepheids were, and remain, the most important tool for measuring cosmic distances beyond what can be measured by geometric methods. It was by observing Cepheid variables in the Andromeda Galaxy, in 1923, that Edwin Hubble was able to establish conclusively that the fuzzy patches of light that astronomers had debated for years, the nebulae, some of which had been proposed to be separate galaxies equal in size to the Milky Way, were indeed immensely distant independent galaxies, vastly larger than anything within the Milky Way and separated from it by distances that stretched the imagination. Before Hubble's measurement, the scale of the universe was unknown. After it, the universe expanded conceptually by a factor of millions. The humble, pulsing Cepheids made this possible. Imagine watching a Cepheid variable over the course of a few weeks. In a small telescope or binoculars, pointed at a known Cepheid, you would see the star visibly brighten, rising to its maximum over the course of perhaps 3 or 4 days, the light increasing noticeably from night to night, the star becoming distinctly brighter than its neighbors in the field of view. Then, more slowly, it would dim, fading over a longer period, descending back through intermediate brightness to its minimum, where it rests briefly before the cycle begins again. The rhythm is patient and unhurried, set not by any external clock but by the physical properties of the star itself, the depth of its helium layer, the strength of its gravity, the temperature at which the ionization transitions occur. The star pulses because it cannot help it. It is the only stable configuration available to it at this stage of its life. Mira variables, by contrast, are red giant stars that pulsate on much longer timescales, periods of months to years, and with less mathematical precision. Mira itself, the prototype of the class, is a red giant in the constellation Cetus that varies between roughly magnitude 2, comfortably visible to the naked eye, and magnitude 10, far below the threshold of naked eye visibility, over a period of approximately 332 days. The amplitude of variation, the difference between maximum and minimum brightness, can be more than 1,000-fold, which is extraordinary by any standard. Watching Mira over the course of a year would be like watching a star appear in the sky, grow brighter than most of the stars visible in that part of the sky, then slowly fade and vanish again. This has been happening for as long as the star has been in this phase of its life, billions of years, perhaps, and it will continue until the star sheds its outer layers entirely and leaves behind a white dwarf. There is another category of variable star whose variability is not intrinsic to the star at all, but is produced by the geometry of the viewing angle. In an eclipsing binary system, 2 stars orbit each other in a plane that is oriented edge-on as seen from Earth. As the stars orbit, each one periodically passes in front of the other, blocking some or all of its companions' light from reaching us. The resulting dip in brightness, an eclipse, repeats with the orbital period and can be measured with great precision. The most famous eclipsing binary is Algol, the second brightest star in Perseus, whose brightness dips noticeably every 2.87 days when its dimmer companion passes in front of its brighter primary. Algol's variability was noted by Arabic astronomers more than 1,000 years ago, and the star's name, derived from the Arabic for the demon's head, may reflect its disturbing tendency to periodically diminish. The monitoring of variable stars is one area of astronomy in which dedicated amateur observers have made, and continue to make, scientifically significant contributions. Organizations such as the American Association of Variable Star Observers maintain archives of millions of observations contributed by amateur astronomers around the world over more than a century, recording the brightness of variable stars on each night of observation. This vast collective database, contributed by people equipped with nothing more than modest telescopes and careful attention, has provided the light curves, graphs of brightness over time, from which professional astronomers derive their measurements of stellar properties. Variable star observers are, in a sense, the long-term monitors of the sky, sitting with their notebooks and their telescopes on cold, clear nights, noting the brightness of faint stars with the same patient regularity that the stars themselves maintain in their pulsations. There is something quietly companionable about this image, a person in a dark field, under the stars, watching a star's slow brightening and fading, night by night, keeping a record that will eventually tell a story about the deep interior of a sphere of gas 1,000 light-years away. The star pulsing. The observer watching. The data accumulating. The universe measuring itself, through the patience of a human eye and notebook. Henrietta Swan Leavitt's discovery of the period-luminosity relation is one of the great intellectual achievements of the 20th century, and one of the great injustices of the history of science. Leavitt worked at the Harvard College Observatory as a human computer, a woman hired to perform the computational labor of analyzing astronomical data, work that was considered unsuitable for the full professional status accorded to male astronomers. Her salary was 25 cents per hour. She worked meticulously through thousands of photographic plates, identifying and cataloging variable stars in the Magellanic Clouds, and in the process made the discovery that unlocked the scale of the universe. When the Swedish mathematician Gösta Mittag-Leffler sought to nominate her for the Nobel Prize in Physics in 1924, he was informed that she had died of cancer 3 years earlier, in 1921, at the age of 53. The prize is not awarded posthumously. R. Lyrae variables are another class of pulsating star, smaller and older than Cepheids, with pulsation periods of less than a day, found predominantly in the ancient globular clusters that orbit the galactic halo. Like Cepheids, they are standard candles. Their intrinsic luminosity is known, so measuring their apparent brightness immediately yields their distance. Because they are found in globular clusters, they were the instruments through which the American astronomer Harlow Shapley, in 1918, mapped the distribution of those clusters and discovered that the Milky Way was far larger than previously thought, and that the Sun was not at its center. The Sun, Shapley showed, sits roughly 2/3 of the way out from the center of the galaxy, a revelation that displaced humanity from the center of the Milky Way, as the Copernican revolution had earlier displaced it from the center of the solar system. The Sun itself is variable, though only slightly. Its total luminosity changes by approximately 0.1% over the 11-year solar cycle, a variation so small that it is undetectable to any human sense, and too small to have a significant direct effect on Earth's climate. But whether the longer-term variation of the Sun, over centuries and millennia, has contributed to historical climate events such as the Little Ice Age is a matter of ongoing research. The Maunder minimum, a period of unusually low sunspot activity between 1645 and 1715, coincided with particularly cold winters in Europe and North America. Whether the reduced solar activity directly caused the cooling, or whether other factors were primarily responsible, remains debated. Long-period variable stars, Mira and her relatives on the asymptotic giant branch, are not merely curiosities of stellar physics. They are among the major sources of enrichment of the interstellar medium. As these stars pulsate and shed their outer layers in great winds of gas and dust, they are returning the products of their nuclear burning to the surrounding space, carbon, nitrogen, oxygen, and the complex molecules that form on the surfaces of the dust grains expelled from their atmospheres. The dust produced by evolved variable stars is a major component of the interstellar dust that dims distant stars and enriches the molecular clouds from which new stars form. Every grain of cosmic dust, every ice-coated particle drifting through interstellar space, contains a memory of the dying star that produced it. There is a poetic quality to variable stars that is easy to sense even without understanding the physics. A star that dims and brightens, over weeks or months, on a schedule as regular as the calendar, it has a rhythm, almost like breath, almost like a heartbeat, the most ancient physiological metaphors mapped onto the most ancient objects in the sky. The Cepheids pulse. The Miras breathe. The RR Lyrae stars flicker. And below them, on a planet they have never noticed, human beings watch with small telescopes on cold clear nights, noting the brightness, comparing it to nearby constant stars, recording the time, adding their observation to a century's worth of accumulated data. The star keeping its rhythm. The observer keeping count. The stars have been keeping their own rhythms long before any eye watched them. They continue now, while yours close. Chapter 7. Binary stars. Most stars are not alone. The Sun, orbiting the center of the Milky Way in a relatively uncrowded region of the galaxy, with no stellar companion within 4.2 light-years, is actually unusual in its solitude. By most estimates, somewhere between half and two-thirds of all stars in the galaxy are members of binary or multiple star systems, gravitationally bound pairs or groups of 2, 3, 4, or occasionally more stars, orbiting around their common center of mass in relationships that may last for billions of years. The night sky, when examined closely enough, is far less a collection of solitary points of light than it appears, and far more a landscape of partnerships and gravitational dances playing out across distances too large and timescales too long for ordinary perception to grasp. Binary stars form primarily in the same way single stars form, from the collapse and fragmentation of molecular clouds, with the difference that when a collapsing cloud fragment develops two dense cores rather than one, each core can condense into a star while remaining gravitationally bound to the other. Whether a particular collapse produces one star or two depends on the angular momentum of the initial cloud fragment, its density distribution, the rate of cooling, and other conditions that vary from cloud to cloud. Computer simulations of star formation consistently produce binary and multiple systems as natural outcomes, and observations of young star-forming regions confirm that the binary fraction among newly formed stars is even higher than among older stellar populations. Many binaries that form close together eventually merge or separate as the system dynamically evolves. The variety of binary configurations is enormous. At the widest extreme are the visual binaries, pairs of stars separated by distances of hundreds or even thousands of astronomical units, in some cases, several light-years, orbiting each other so slowly that a single orbital period may take 1,000,000 years or more. The orbital motion of these stars is far too slow to observe directly in a human lifetime. Their binary nature is inferred from the fact that both stars share the same position in space and the same motion through the galaxy, and from parallax measurements that confirm they are at the same distance. At the closest extreme are contact binaries, pairs of stars so close together that their outer gas envelopes actually touch and merge into a shared envelope, the two stellar cores embedded in a common atmosphere of gas, exchanging material continuously. The gravitational dance of a binary system is described beautifully by Newtonian mechanics. The two stars orbit their common center of mass, the point between them where, if you imagined a seesaw, the system would balance, in elliptical orbits whose sizes are inversely proportional to the stellar masses. The more massive star orbits closer to the center of mass, the less massive star farther away, but both complete each orbit in exactly the same period. From far away, the center of mass moves in a straight line through space while both stars revolve around it. The system traces a stately, regular pattern, two bodies performing the same waltz, step for step, period after period, for billions of years. When the stars in a binary system are close enough together, they influence each other in ways that go beyond simple gravitational attraction. The gravity of each star raises tidal forces on the other, distorting the stellar shape into a slight elongation pointed toward the companion. In very close binaries, this tidal distortion can be significant. Both stars may be noticeably elongated, egg-shaped rather than spherical. The tidal forces also tend to synchronize the rotation of each star with the orbital period, in the same way that the Moon has been tidally locked to the Earth so that it always shows the same face. In a close binary system, both stars may rotate with periods equal to the orbital period, each always presenting the same face to its companion. Imagine living on a planet in such a system, two suns in the sky, always in the same positions relative to each other, one always slightly above and to the left of the other, perhaps, as the planet orbits in a stable configuration around both. The day and the year might be intimately intertwined. As stars age and evolve off the main sequence, the interactions between binary companions become more dramatic. When the more massive star of a pair expands into a red giant, its outer envelope may grow so large that it overflows what is called its Roche lobe, the region of space within which its own gravity is stronger than the companion's gravitational pull. Material at the edge of the Roche lobe is on the gravitational border between the two stars, and once the giant's envelope extends beyond this boundary, gas begins to stream from one star to the other. This process, called mass transfer, fundamentally changes the evolution of both stars. The giant loses mass, which slows its evolution and may eventually shrink it back to a more compact configuration. The companion, gaining mass, may be spun up to rapid rotation, heated, and fundamentally altered in its own evolution. In many binary systems, the mass transfer occurs not into the companion star itself but into a disk of gas that forms around it, an accretion disk, a swirling, spiraling sheet of material that gradually falls inward onto the stellar surface. In systems where the accreting star is a white dwarf, this process can produce spectacular periodic explosions called novae. As hydrogen-rich gas accumulates on the surface of the white dwarf, it eventually reaches the temperature and pressure required for hydrogen fusion, not sustained, controlled fusion in a core, but a sudden, explosive surface ignition that blasts the accumulated layer into space in a flash of light visible across thousands of light-years. The nova brightens dramatically over days, then fades over weeks or months, as the expelled material thins and cools. The white dwarf itself survives, the accretion disk reforms, and the process may eventually repeat after years or decades. The Alpha Centauri system, our nearest stellar neighbor, is itself a triple system. Alpha Centauri A and B are a visual binary, two stars similar in mass and type to the Sun, orbiting each other at a separation roughly equal to the distance between the Sun and Uranus, with a period of about 80 years. They are close enough that the orbital motion of each is visible over a human lifetime. An astronomer who spent a career observing them would see both stars shift meaningfully in position relative to each other. Orbiting far from this pair, at a distance of about 13,000 astronomical units, is Proxima Centauri, the small red dwarf that is, at this particular moment in the galaxy's history, the closest star to the Sun, though that distinction changes over millions of years as all the stars move. The three-body system is gravitationally stable, but only barely. Perturbations over millions of years may eventually unbind Proxima from the system. Across the galaxy, billions of such partnerships are playing out in silence, stars orbiting each other, exchanging mass, tidally distorting each other, flaring in shared novae, gradually evolving and dying in configurations that involve more than one player. No star exists entirely apart from the gravitational influence of everything else, but some are more intimately entangled than others. The night sky, from the outside, looks like a collection of separate points. From the inside, it is full of pairs. When two stars in a binary system are too close together to be resolved as separate points of light even by the largest telescopes, their binary nature can still be detected by the technique of spectroscopic binaries. As the two stars orbit each other, their radial velocities relative to Earth change continuously. When one star is moving toward Earth and the other is moving away, the Doppler shift separates their spectral lines into two sets, one shifted blue, one shifted red, that oscillate back and forth with the orbital period. By measuring this oscillation, astronomers can determine the orbital period, the minimum masses of the stars, and the shape of the orbit, from a spectrum of the combined light that shows no spatial resolution of the two objects at all. Many of the binary systems now known were identified first as spectroscopic binaries, their duplicity revealed entirely by the motion of their spectral lines. The three-body problem, the question of predicting the long-term motion of three gravitationally interacting bodies, is one of the oldest unsolved problems in classical mechanics. Two bodies orbit each other predictably, in ellipses that can be calculated exactly. Three bodies interact in ways that are, in general, chaotic. Tiny changes in the initial conditions lead to wildly different outcomes over long timescales, and no general closed-form solution exists. For triple-star systems, this means that the long-term stability of the system depends sensitively on the configuration, the ratios of the masses and the separations. Many triple systems are stable in a hierarchical configuration, a close inner pair orbited by a third star at a much greater distance. In these systems, the outer star's orbit is only weakly perturbed by the inner pair, and the system can persist for billions of years without dramatic changes. Others are unstable, and the eventual ejection of one star from the system, leaving behind a binary, is the long-term outcome. The detection of gravitational waves has opened a new window on binary stellar systems. When two compact objects, neutron stars, black holes, or combinations of these, spiral inward toward each other as their orbit decays through the emission of gravitational radiation, the waves they produce can be detected on Earth by instruments of extraordinary sensitivity. The first gravitational wave detection, announced in February 2016 by the LIGO collaboration, was the signal from two merging black holes approximately 1.3 billion light-years away, objects of 36 and 29 solar masses, orbiting each other at close to half the speed of light in their final moments, the collision lasting a fraction of a second and releasing more energy in gravitational waves than all the stars in the visible universe emit in light. The signal, when converted to sound, is a brief chirp, rising in pitch and amplitude to a peak, then silence. Whether planets can form and persist in binary star systems is a question of great practical importance for astrobiology. Close binary systems, where the two stars are separated by less than about a quarter of an astronomical unit, can host planets in stable orbits around both stars simultaneously, circumbinary planets, orbiting outside the binary pair, and several such planets have been detected by the Kepler Space Telescope, their transits producing the characteristic double-dip-like curves that betray the presence of two suns rather than one. From the surface of such a planet, the sky would host two suns, sometimes close together, sometimes separated by a significant angle, their combined light varying with the orbital phase, the landscape illuminated in shifting patterns of color and shadow as the two different colored stars moved across the sky. Across the galaxy, billions of such partnerships are playing out in silence, stars orbiting each other, exchanging mass, tidally distorting each other, flaring in shared novae, gradually evolving and dying in configurations that involve more than one player. No star exists entirely apart from the gravitational influence of everything else, but some are more intimately entangled than others. The night sky, from the outside, looks like a collection of separate points. From the inside, it is full of pairs. The universe is less solitary than it appears. Rest in the company of it. Chapter 8: Red Giants. Every star on the main sequence is in a state of balance. The energy produced by nuclear fusion in the core pushes outward as radiation pressure, while the gravitational weight of all the overlying gas pushes inward. For as long as there is hydrogen to fuse, this balance holds, and the star remains stable, neither growing nor shrinking, neither brightening dramatically nor dimming, simply shining at a luminosity and temperature determined by its mass, for a duration determined by how much hydrogen it contains and how fast it burns it. But hydrogen is not infinite, and gravity is patient. Eventually, in the innermost core of the star, the hydrogen runs out. And when it does, the balance breaks, and the star begins the most dramatic transformation of its long life. The process begins quietly. As the hydrogen in the core is consumed, the core becomes increasingly enriched in helium, the ash of the fusion reactions, which sits inert and unburnable at the temperatures available. Without fusion to produce energy, the core loses the radiation pressure that was holding it up against gravity. The core contracts. As it contracts, it heats. The rising temperature of the contracting helium core spreads outward, heating the shell of hydrogen-rich gas just above the core to temperatures sufficient for hydrogen fusion. Fusion begins in this shell, not in the core, but in a thin layer surrounding it, and proceeds at a rate that produces far more energy than the original core fusion did. This excess energy inflates the outer layers of the star. The star begins to grow. It grows slowly at first, and then with gathering speed, as the shell burning intensifies and the energy output rises. The outer layers, expanding and cooling as they spread into a larger volume, become cooler and redder. The surface temperature falls from the yellowish 5,500 degrees of a sun-like star at its prime to perhaps 3,500 degrees, shifting the peak emission from yellow-green toward deep red. The star becomes a red giant. Its radius, which was once similar to the Sun's, roughly 700,000 kilometers, may grow to 50 times, 100 times, even 200 times that value, swallowing the orbits of the inner planets if any exist. The surface gravity, spread across a sphere hundreds of times larger in radius, decreases to a small fraction of its main sequence value, and the tenuous outer layers are barely bound to the star at all. Aldebaran, the orange giant that forms the Eye of Taurus the Bull and is one of the brightest stars in the night sky, is a red giant of modest size, perhaps 44 times the Sun's radius. Arcturus, the bright orange star that anchors the constellation Boötes and is the fourth brightest star in the night sky, is approximately 25 times the Sun's radius. Betelgeuse, the enormous red supergiant that marks the right shoulder of Orion, is of a different scale entirely, roughly 700 times the radius of the Sun, so large that if it were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. These are the evolved descendants of stars more massive than the Sun, which leave the main sequence more quickly and expand more dramatically, but the same process, hydrogen shell burning, expanding envelope, cooling surface, drives the transformation of stars of all masses when their core hydrogen is finally exhausted. For the Sun, specifically, the red giant phase will arrive in approximately 5 billion years. The transformation will be gradual by human standards. The Sun will slowly brighten and grow over hundreds of millions of years, but ultimately it will swell to perhaps 200 times its current radius. The Earth's oceans will have evaporated long before this point, heated beyond boiling by the increasing solar luminosity, and the inner solar system will be a barren, scorched environment. Whether the Sun's expanding envelope will ultimately engulf the Earth's orbit is a question that depends on the uncertain details of how the Sun sheds mass as it expands, a process that could cause the Earth's orbit to drift outward fast enough to stay ahead of the solar surface. The outcome is genuinely uncertain, and no one currently alive will be around to see it. Within the red giant, the helium core continues to contract and heat. The electrons in the core are compressed into a state of quantum degeneracy, a state in which the Pauli exclusion principle prevents further compression by creating a pressure that does not depend on temperature. The core is held up not by thermal pressure, as in ordinary gas, but by electron degeneracy pressure. This is a strange and important state of matter because in a degenerate gas, temperature and pressure are decoupled. Adding heat does not increase the pressure. This has dramatic consequences when the core finally reaches the temperature needed to fuse helium. At approximately 100 million Kelvin, helium nuclei can fuse together in what is called the triple alpha process, 3 helium nuclei combine to form a carbon-12 nucleus, and the carbon can then capture a 4th helium nucleus to produce oxygen. This reaction requires 3 particles to come together very nearly simultaneously, an event of low probability, and it was long a puzzle why the universe contains as much carbon as it does, given how improbable the triple alpha process appeared to be. In 1952, the British astrophysicist Fred Hoyle predicted that for the triple alpha process to occur at the observed rate, the carbon nucleus must have an excited energy state at precisely the right energy level to resonate with the reaction products. He was correct, and the predicted resonance was subsequently measured in the laboratory. It was one of the most audacious predictions in the history of astrophysics, predicting a nuclear property of an atom from the fact that carbon-based life exists to ask the question. In the degenerate helium core of a red giant, helium fusion ignites not gradually but explosively, in an event called the helium flash. Because the degenerate core does not expand when heated, the pressure is determined by the quantum state of the electrons, not the temperature. The initial onset of helium fusion raises the temperature without relieving the pressure. The higher temperature increases the fusion rate, which raises the temperature further, in a runaway that releases, within a few seconds, more energy than the sun emits in billions of years. Yet none of this is visible from outside the star. The energy of the helium flash is entirely absorbed by the outer layers of the red giant, and the star brightens only slightly and settles into a new, quieter configuration, steady helium burning in the core, supported this time by thermal pressure rather than degeneracy. The most violent event in the star's life passes unnoticed. What follows is a period of relative stability, the horizontal branch of the Hertzsprung-Russell diagram for low-mass stars, in which the star burns helium in its core for perhaps 100 million years. This is far shorter than the main sequence hydrogen-burning phase, because helium fusion releases less energy per unit mass than hydrogen fusion, and because the star's luminosity is substantially higher. Eventually the helium in the core runs out, the core becomes inert carbon and oxygen, and the star ascends the asymptotic giant branch, swelling again, brightening again, pulsating and shedding mass in great winds of gas and dust that flow outward from the surface and form a beautiful expanding shell around the dying star. Red giants are among the major contributors to the chemical enrichment of the interstellar medium. As they pulsate and shed their outer envelopes, they drive powerful stellar winds, outflows of gas moving at tens of kilometers per second, carrying with them the products of the star's nuclear burning. For stars that have passed through the helium-burning phase and ascended the asymptotic giant branch, the winds are particularly rich in carbon and the products of reactions involving carbon, nitrogen, the S-process elements produced by the slow capture of neutrons onto existing nuclei. These winds gradually enrich the interstellar gas around the dying star, and the material eventually mingles with a wider interstellar medium, becoming part of the next generation of molecular clouds and the next generation of stars. Asteroseismology, the study of sound waves in stars other than the Sun, has revealed that red giants are among the most informative objects in the stellar sky. Because red giants are intrinsically luminous and therefore visible at great distances, they are detected in large numbers by photometric surveys such as the Kepler and TESS space missions. The oscillations of a red giant, driven by the same convective turbulence that produces granulation on the solar surface, can be detected as subtle periodic changes in the star's total brightness, and from the frequencies of these oscillations, the stellar radius, mass, and interior structure can be precisely determined. Asteroseismology has provided measurements of stellar ages and properties for hundreds of thousands of red giants across the galaxy, making them invaluable traces of galactic structure and history. Betelgeuse, the supergiant that marks Orion's shoulder, has provided a remarkable demonstration of stellar variability in recent years. In late 2019 and early 2020, the star dimmed dramatically, falling to its faintest level in recorded history, dropping from its typical brightness by about 2.5 magnitudes, becoming noticeably dimmer than usual even to casual observers. The event was dubbed the Great Dimming of Betelgeuse, and it prompted widespread speculation about whether the dimming was the precursor to a supernova explosion. It was not. The dimming was subsequently understood as the result of a mass ejection that produced a large cloud of cool dust in the line of sight from Earth, temporarily blocking the star's light. Betelgeuse recovered its typical brightness within a few months. But the event served as a reminder of how variable and unpredictable these enormous, dynamic stars can be, and how much there is still to learn about the late stages of massive stellar evolution. The planetary nebulae produced by dying low-mass stars are among the most aesthetically striking objects in the universe. They come in an extraordinary variety of shapes: spherical shells, bipolar lobes like hourglasses, multi-ringed structures, spirals, knotted and filamentary structures that reveal the turbulent history of the mass loss process. The Ring Nebula in Lyra, a classic example, appears through a small telescope as a small smoke ring, a glowing oval of light with a faint central star visible at its core. The Helix Nebula in Aquarius, sometimes called the Eye of God for its resemblance to an eye in wide-field photographs, is one of the closest planetary nebulae to Earth, roughly 655 light-years away, its apparent diameter on the sky roughly half that of the full moon. These objects last only a few tens of thousands of years before the expanding shell becomes too diffuse to glow, brief and beautiful epilogues to the long lives of the stars that produced them. The red giant phase is the beginning of the end, stretched across hundreds of millions of years. It proceeds in its own time, without urgency. As all things end, when they are ready. Chapter 9: The Death of a Star. A star the mass of the Sun does not die with a bang. It dies slowly, over hundreds of millions of years, shedding its outer layers in a long, gentle exhalation that spreads the material of its atmosphere into a glowing shell of gas and dust expanding outward into the surrounding space. These shells, planetary nebulae, so named by William Herschel in the 18th century because some of them resembled the round disk of a planet when seen through the telescopes of his time, are among the most beautiful objects in the universe and among the most misnamed. They have nothing to do with planets. They are the outer atmospheres of dying stars, illuminated from within by the hot, exposed core that the departing gas has left behind. As the red giant on the asymptotic giant branch pulses and sheds mass in successive outflows of gas, the accumulated losses gradually strip away the outer layers. The rate of mass loss can be extraordinary in the final stages. Some asymptotic giant branch stars are losing the equivalent of an Earth mass every 10 years or so, blown away by stellar winds and the radiation pressure of their own light. As the outermost layers depart, they expose progressively hotter and denser layers beneath. The core, which has been accumulating the ashes of successive fusion stages, first the carbon and oxygen from helium burning, is gradually uncovered. When the departing shell is far enough away, the remaining core, now intensely hot and dense, floods the surrounding gas with ultraviolet radiation, causing it to glow in the characteristic colors of ionized gas, the green of doubly ionized oxygen, the red of hydrogen alpha emission, the blue of ionized nitrogen. The planetary nebula lights up. What remains at the center of the nebula, the object that has shed its outer layers and now glows at the heart of the expanding shell, is the white dwarf. It is the exposed core of the former star, a sphere roughly the size of the Earth, compressed to a density of approximately 1,000,000 grams per cubic centimeter, so dense that a teaspoon of its material would weigh roughly 5 tons on Earth's surface. A white dwarf is made primarily of carbon and oxygen, the products of helium burning, though its surface is typically covered by a thin layer of hydrogen or helium, whatever was left at the end of the star's active life. The temperature of a newly formed white dwarf can exceed 100,000 Kelvin, making it one of the hottest objects in the galaxy, though its small surface area means its total luminosity is modest. A white dwarf is supported against gravitational collapse not by thermal pressure, it has no fusion reactions producing energy, but by electron degeneracy pressure. The electrons in the compressed white dwarf cannot be confined to smaller spaces without violating the Pauli exclusion principle, the quantum mechanical rule stating that no two electrons can occupy the same quantum state. This rule creates a pressure that resists compression regardless of temperature, and it is this quantum mechanical pressure that holds the white dwarf up. Without fusion, the white dwarf has no energy source, and it cools very slowly over billions of years, remaining hot for billions of years because it is so dense that heat escapes from it only slowly, like a very massive brick removed from an oven. The white dwarfs we observe in the galaxy today range from young ones, still hot and glowing brilliantly, to old ones that have faded to dim orange. No white dwarf in the galaxy has yet had time to cool to the theoretical endpoint, the black dwarf, a cold, dark remnant, because the universe is not yet old enough. But white dwarfs are only the fate of stars with masses up to roughly 8 times the mass of the Sun. For stars more massive than this threshold, the story ends differently, and far more violently. A massive star burns through its hydrogen fuel in millions rather than billions of years, spending its entire main sequence life at a furious pace, shining with a luminosity tens of thousands of times greater than the Sun. When the hydrogen in the core is exhausted, the core contracts and heats, igniting helium fusion, but now the temperature rises high enough not only to fuse helium but, subsequently, carbon, neon, oxygen, and finally silicon. Each successive fusion fuel produces a denser, hotter core of heavier elements, surrounded by shells of lighter elements still burning. The star develops a layered structure like a cosmic onion, a silicon-burning core, surrounded by an oxygen-burning shell, surrounded by carbon, neon, helium, and hydrogen shells. The fusion sequence ends with iron. The nucleus of iron 56 is the most tightly bound nucleus in nature. It represents the valley of the energy landscape of nuclear physics, the configuration from which neither fusion nor fission can extract net energy. When the silicon-burning shell surrounding the iron core converts its last silicon into iron, the iron core can do nothing but accumulate. It grows, fed by the silicon burning above it, approaching the Chandrasekhar limit, roughly 1.4 times the mass of the Sun, the maximum mass that electron degeneracy pressure can support. When the iron core exceeds this limit, the collapse begins. What happens in the next second is the most violent event in the known universe short of the Big Bang. The iron core collapses at 1/4 of the speed of light, compressed from the size of the Earth to the size of a city, roughly 20 kilometers across, in less than a second. At nuclear densities, neutron degeneracy pressure abruptly halts the collapse, and the infalling outer layers bounce off the suddenly rigid core, generating a shock wave that propagates outward through the star. The shock wave, powered by an enormous burst of neutrinos produced as electrons and protons in the core merge to form neutrons, rips through the star's outer layers and ejects them into space in a supernova explosion. The expanding debris cloud, enriched with the products of decades of nuclear burning, including newly synthesized elements heavier than iron, glows for weeks with a luminosity comparable to that of its entire host galaxy. The object left behind at the center of the supernova remnant is a neutron star, a sphere of approximately 20 kilometers in diameter, containing 1 to 2 times the mass of the Sun, made almost entirely of neutrons packed to nuclear density. The surface gravity of a neutron star is about 100 billion times that of the Earth's surface. Its density is comparable to that of an atomic nucleus. A neutron star formed in a supernova is typically spinning very rapidly, the conservation of angular momentum amplifying the slow rotation of the original star's core as it collapses by a factor of billions, and carrying an intense magnetic field. As it spins, the magnetic field sweeps 2 beams of radio emission across the sky. If one of these beams sweeps past the Earth with each rotation, we detect the star as a pulsar, a source of radio pulses as regular as an atomic clock, repeating at intervals ranging from a few seconds to milliseconds, each pulse marking another rotation of the neutron star. The remains of the stellar lives, the white dwarfs and neutron stars and the expanding clouds of gas enriched with heavy elements, are not the end of the story. They are the beginning of the next one. The first white dwarf ever recognized as such was hiding in plain sight, next to the brightest star in the night sky. Sirius, Sirius A, to be precise, has a companion, discovered in 1862 by the American telescope maker Alvin Graham Clark while testing a new 18-inch lens he had just built. The companion, Sirius B, was far dimmer than its neighbor but unexpectedly hot, a puzzle, because hot objects are generally also luminous, and Sirius B was not. When the nature of white dwarfs was finally understood in the 1920s and 1930s, the resolution became clear. Sirius B was hot because it was a remnant stellar core, still radiating the heat of its formation, but its small size meant its total luminosity was modest despite its high surface temperature. The existence of Sirius B, a stellar corpse tucked within one of the most observed star systems in history, had been unsuspected for centuries. The Chandrasekhar limit, 1 point for solar masses, the maximum mass a white dwarf can sustain, was derived by the Indian-American astrophysicist Subrahmanyam Chandrasekhar in 1930, at the age of 19, during a sea voyage from India to England. Using relativistic quantum mechanics, he calculated that for white dwarfs above this critical mass, electron degeneracy pressure would be insufficient to halt collapse. The result was initially rejected by the British astrophysicist Arthur Eddington, the most eminent astronomer of the day, who found it physically unacceptable and publicly ridiculed Chandrasekhar's work. The disagreement was never fully resolved in Eddington's lifetime, but Chandrasekhar was eventually vindicated, and eventually awarded the Nobel Prize in Physics, in 1983, 53 years after his sea voyage calculation. When a white dwarf in a binary system accretes enough mass from a companion to approach the Chandrasekhar limit, the consequences are different from those of a collapsing stellar core. As the white dwarf mass nears the critical limit, the increasing pressure and temperature eventually ignite a thermonuclear runaway in the degenerate carbon-oxygen interior, a type Ia supernova. Because the white dwarf is always near the same mass when this occurs, type Ia supernovae are approximately standard candles. They all reach approximately the same peak luminosity, and by measuring how bright they appear from Earth, their distances can be calculated. It was through observations of type Ia supernovae in distant galaxies in the late 1990s that two teams of astronomers independently discovered that the expansion of the universe is accelerating, driven by a mysterious dark energy that remains one of the deepest puzzles in physics. Neutron stars exhibit properties of matter at extremes that no laboratory on Earth has yet been able to replicate. Their interior density is roughly equivalent to compressing the mass of the Sun into a sphere the size of a small city. At these densities, atomic structure has completely ceased to exist, protons and electrons have merged into neutrons, and the neutrons themselves are packed so closely that they may overlap, producing exotic states of matter described by theories that remain unconfirmed: strange quark matter, color superconductors, pion condensates. A neutron star's surface gravity is perhaps 100 billion times Earth's. Its escape velocity is roughly half the speed of light. The curvature of spacetime at its surface is sufficient to bend light dramatically. You could, in principle, see more than half of a neutron star's surface simultaneously, because the gravitational lensing curves light around from the far side. Among the most extreme neutron stars are the magnetars, objects with magnetic fields measured in units of 10 to 15 Tesla, many billions of times stronger than the fields of ordinary pulsars. Magnetars are thought to form in particularly energetic supernova explosions, or in specific conditions of rapid rotation in the progenitor star. They are among the most active objects in the universe. They occasionally produce intense bursts of X-rays and gamma rays as their powerful magnetic fields shift and crack the neutron star's rigid crust. The most powerful magnetar flare ever recorded, on the 27th of December, 2004, was so energetic that it caused detectable ionization of Earth's upper atmosphere from a distance of 50,000 light-years from the other side of the galaxy. The universe recycles everything. Rest in that long continuity. Chapter 10, Supernovae. On the 23rd of February, 1987, at a neutrino detector buried deep beneath the surface of the Earth in a Japanese zinc mine, a brief and extraordinary event occurred. In the span of approximately 12 seconds, the Kamiokande 2 detector recorded 11 particle interactions that its operators identified as the signature of electron antineutrinos, a burst of particles so faint and so rarely detected that the facility might typically record 1 or 2 in a month of continuous operation. Within hours, similar detectors in Ohio and in Russia reported their own bursts of detections. Approximately 3 hours later, observers in the southern hemisphere noticed that a faint star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, roughly 168,000 light-years away, had brightened dramatically. By the following day, the object was visible to the naked eye. A massive star had died, and the universe had sent notice of its death in neutrinos, 3 hours before the light of the explosion arrived. The event, designated SN 1987A, was the closest supernova observed since Kepler's supernova of 1604 and the first to be detected in neutrinos. It provided an extraordinary confirmation of the theoretical picture of core collapse supernovae, the burst of neutrinos, carrying roughly 99% of the total energy of the explosion, was detected before the optical brightening because neutrinos, interacting so weakly with matter, escaped the stellar envelope almost instantaneously after the core collapse, while the shockwave carrying the optical light took several hours to travel outward through the overlying layers of the star. The sequence of detection, neutrinos first, light 3 hours later, was precisely what the theory predicted. Supernovae are the most energetic events in the universe between stellar scales and the scale of the Big Bang itself. A core collapse supernova releases approximately 3 times 10 to the power of 44 joules of energy in total, roughly 100 times the energy our Sun will emit over its entire 10 billion-year lifetime, released in seconds. The vast majority of this energy, perhaps 99%, is carried away by the neutrino burst. The optical explosion, the brilliant display that makes a supernova briefly visible across the galaxy and sometimes across the universe, represents only about 1% of the total energy. That 1% is still sufficient to outshine the entire galaxy of hundreds of billions of stars for weeks. The material ejected in the supernova explosion carries with it the products of all the nuclear burning stages through which the star passed in its life. The outer hydrogen envelope records the original composition of the star. Beneath it are layers of helium, carbon, oxygen, neon, silicon, and finally the iron that brought the fusion sequence to its end. Mixed into all of these layers by the turbulence of the explosion are freshly synthesized elements, including those heavier than iron, which are produced in the intense neutron fluxes that accompany the core collapse and the early stages of the explosion. Gold, silver, platinum, uranium. These elements cannot be made in ordinary stellar burning. They require the extraordinary conditions of a supernova, or, as more recent research has revealed, the even more extreme conditions of a neutron-star merger, in which 2 neutron stars spiral together, collide, and produce a kilonova. In 2017, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves from the merger of 2 neutron stars in a galaxy 130 million light-years away. Simultaneously, observatories around the world detected the electromagnetic counterpart, the kilonova, and found in its spectrum the signatures of freshly synthesized gold and other heavy elements. The observation confirmed that neutron-star mergers are a major source of the heaviest elements in the universe. The gold in any ring, in any bank vault, in any tooth filling, on any planet anywhere, was almost certainly produced in either a supernova or a neutron-star merger, at some point in the history of the universe before the formation of our solar system. The iron in your blood was fused in the dying core of a massive star that exploded long before the Earth formed. The calcium in your bones was synthesized in the explosive silicon burning phases of a stellar death. The oxygen you breathe, much of it, was produced in stellar fusion and distributed by stellar winds and supernovae. The carbon of which your body is largely built was made in the helium-burning cores of red giants. You are, in the most literal and chemical sense, composed of the ashes of dead stars. Not metaphorically. Not poetically. You are, the atoms in your body were in stars that no longer exist, and they arrived in the molecular cloud from which the solar system formed, and they became part of the Earth, and eventually part of the food chain, and eventually part of you. The expanding debris of supernovae is not lost. It disperses through the surrounding interstellar medium, enriching it with heavy elements. It compresses nearby molecular clouds, sometimes triggering the gravitational collapse that initiates a new generation of star formation. The next generation of stars to form from that cloud will contain the heavy elements produced by the supernova. Their planets, if they form planets, will contain the iron and silicon and calcium and gold that the supernova synthesized. Life, if it arises on those planets, will be built from those elements. The supernova death of one star is woven directly into the birth of the next generation. Some supernovae leave behind no stellar remnant at all, or rather, the remnant immediately collapses further, through neutron degeneracy pressure, into a black hole, the region of space where the escape velocity exceeds the speed of light, and from which nothing, not even the photons that carry all the information we depend on, can return. A stellar mass black hole has a radius of a few kilometers, smaller than a city, but a gravitational field so extreme that even the space itself is curved by it, and the flow of time near the event horizon is measurably slower than far away. Black holes formed in supernova collapses are entirely dark. They can be detected only through their gravitational effects on surrounding matter, the X-rays emitted by gas accreting onto them from a binary companion, or the gravitational waves produced when two black holes merge. Across the galaxy, a core collapse supernova occurs roughly once or twice per century. One has not been visible to the naked eye in our galaxy since 1604, though several have been observed in the aftermath of their explosion by telescopes, their remnants glowing in X-rays and radio waves. The next naked-eye supernova in the Milky Way could occur at any time, perhaps tonight, perhaps in 1,000 years. When it does, it will be unmistakable, a new brilliant star, rivaling or surpassing the Moon in brightness, visible in daylight, the brief and dazzling announcement of a stellar death that has been in preparation for millions of years. Until then, the supernovae of distant galaxies continue, unseen except by telescopes, distributing the elements of the next generation of stars across the universe. The historical records of supernovae visible to the naked eye span many cultures and many centuries. Chinese court astronomers, whose duty included the meticulous recording of unusual heavenly phenomena, documented what they called guest stars, stars that appeared where none had been before and then gradually faded. The supernova of 1054, whose remnant is now known as the Crab Nebula, was recorded by Chinese astronomers as a guest star visible in daylight for 23 days and at night for nearly 2 years. It may also have been observed by astronomers in Japan and in the Islamic world, and possibly by Native Americans in the American Southwest, where rock art at several sites shows a crescent moon adjacent to a bright star, a configuration that matches the position of the moon relative to the supernova on the morning of its appearance. No European record has been found, perhaps because the star appeared near the sun in the sky in the early weeks when it would have been most easily noticed in the pre-dawn sky. The Crab Nebula today, nearly 1,000 years after the explosion, is a cloud of gas roughly 11 light-years across, still expanding at about 1,500 kilometers per second. At its center lies the Crab Pulsar, the neutron star produced by the collapse, spinning 30 times per second, sweeping 2 beams of radiation across the sky, and still powering the nebula's luminosity through the injection of high-energy electrons and positrons into the surrounding gas. The Crab Nebula is one of the most intensively studied objects in the sky precisely because the date of its formation is precisely known, making it possible to observe the evolution of a supernova remnant over human timescales. Comparing observations made decades apart reveals the expansion of the nebula's filaments and the evolution of its interior structure. A supernova remnant does not merely glow. It actively reshapes the surrounding interstellar medium, driving a shock wave outward into the surrounding gas and dust, compressing it, heating it, accelerating cosmic rays, high-energy charged particles that travel through the galaxy at nearly the speed of light and contribute to the ionization of the interstellar medium. The shock wave can trigger the collapse of nearby molecular cloud regions, initiating a new round of star formation in a cascade of stellar birth and death that may propagate through a galactic arm over millions of years. The solar system may itself have been triggered into formation by the shock wave of a supernova explosion in the vicinity of the presolar cloud. There is isotopic evidence in ancient meteorites for the recent injection of supernova material into the solar nebula just before its collapse began. Consider what a supernova has given you. The iron in your blood, synthesized in the silicon-burning cores of massive stars and distributed by their explosions. The calcium in your bones, made in explosive nucleosynthesis during core collapse. The iodine in your thyroid, produced in supernova events and incorporated into the molecular cloud from which the solar system formed. The oxygen you breathe, produced in stellar interiors and stellar winds and supernovae, mixed into the interstellar medium over billions of years of stellar cycling. You are not merely descended from stars in a poetic sense. You are literally assembled from the ashes of specific stellar death events that occurred before the solar system existed, whose material was incorporated into the presolar cloud and distributed into the bodies of every planet and every organism on this world. Type Ia supernovae, because they are standard candles, have been used to map the expansion history of the universe across billions of light-years. In 1998, the teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees compared the observed brightness of Type Ia supernovae at various redshifts to what would be expected if the universe were decelerating under the influence of gravity alone. They found, to their considerable surprise, that the distant supernovae were dimmer than expected. They were further away than a decelerating universe would predict. The expansion of the universe, instead of slowing down as expected, was speeding up. Something was driving the expansion faster with time. That something was given the name dark energy, and it remains the largest component of the universe's energy budget, approximately 68% of everything, and one of the most profound mysteries in modern cosmology. The stars give everything, in the end. Rest now in what they have given. Chapter 11, The Quiet Stars. The stars you can see on a clear, dark night number in the thousands. The brightest and most prominent, Sirius, Arcturus, Vega, Rigel, Capella, are the ones that dominate the sky, the ones around which the constellations are organized, the ones that navigators and poets and astronomers have named and studied for thousands of years. They are, by and large, extraordinary objects, massive, luminous, hot, brilliant enough to be visible across hundreds or thousands of light-years of space. They represent the most dramatic fraction of stellar diversity, the celebrities of the galaxy, exceptional in their visibility and therefore overrepresented in our perception of what stars are. But they are not typical. Not even close. The most common type of star in the galaxy is one you cannot see without a telescope, and even then only if you know exactly where to look, the red dwarf, a small, cool, dim star with a mass anywhere from approximately 1/13 to 1/2 the mass of the Sun. Red dwarfs, formerly classified as M-type stars on the spectral sequence, make up roughly 70 to 80% of all stars in the Milky Way by number. They shine with a reddish or orange glow, their surface temperatures ranging from approximately 2,500 to 4,000 Kelvin, and they produce light primarily in the red and infrared portions of the spectrum. Even the closest and therefore brightest red dwarf visible from Earth, Proxima Centauri, a mere 4.24 light-years away, glows at a magnitude of about 11, far too dim for the naked eye, requiring a moderate-sized telescope to be seen. What makes red dwarfs remarkable is not their brightness but their longevity. A star's lifespan on the main sequence is inversely related to its mass. The more massive a star, the faster it burns its fuel and the shorter its life. A star 10 times the mass of the Sun lives for perhaps 10 million years before exhausting its hydrogen. The Sun itself, as we have discussed, has a main sequence lifetime of approximately 10 billion years. But a red dwarf with 1/10 the mass of the Sun burns its hydrogen so slowly, partly because the fusion rate is lower at the lower core temperatures, and partly because red dwarfs are so thoroughly convective that they stir fresh hydrogen from their outer layers into the core throughout their lives, giving the core access to the entire hydrogen reservoir of the star, that it may remain on the main sequence for 1 to 12 trillion years. 1 trillion years. The current age of the universe is approximately 13.8 billion years. A freshly formed red dwarf today has barely begun its life. Not a single red dwarf that has ever formed anywhere in the universe has yet had time to die. Every red dwarf ever created is still shining, still burning hydrogen at its slow and steady rate, in whatever corner of whatever galaxy it occupies. They are the oldest living things in the cosmos, or rather, they are the oldest things that have not yet had time to become something else. Red dwarfs are also, interestingly, the most common hosts of planetary systems, based on current exoplanet statistics. They frequently have rocky planets orbiting within their habitable zones, the regions where liquid water could exist on a planetary surface. However, their habitable zones are very close to the star, typically much closer than Mercury's orbit around the Sun, and planets in these zones are likely to be tidally locked, one face always pointing toward the star, the other always facing away, with a potentially violent boundary between perpetual day and perpetual night. The star itself can be highly variable in its activity, with powerful flares that could strip the atmosphere from a nearby planet over geological timescales. Whether life could arise and persist on a planet orbiting a red dwarf is one of the most actively debated questions in astrobiology, and one that we have not yet been able to resolve observationally. Below even the red dwarfs on the mass scale are the brown dwarfs, objects that occupy the blurry boundary between very low-mass stars and very large planets. Brown dwarfs have masses between approximately 13 and 80 times the mass of Jupiter, or roughly 1 to 8% of the Sun's mass. They are too small and their cores too cool to sustain the proton-proton fusion chain that powers ordinary stars. Some of the most massive ones may fuse deuterium or lithium for a brief period in their youth, but this fuel is quickly exhausted. Brown dwarfs do not shine by nuclear fusion in the sustained sense, they glow primarily by radiating the heat of their initial gravitational contraction, cooling gradually over billions of years. In their youth they are dim reddish objects detectable in the infrared, in their old age they cool toward temperatures comparable to a mild oven, emitting most of their radiation at wavelengths invisible to the human eye. The number of brown dwarfs in the galaxy is uncertain but probably large, perhaps comparable to the number of ordinary stars, though because of their dimness they are difficult to detect and census. Between the stars of our galaxy, among the dark spaces that appear empty on any map, there are almost certainly many thousands of brown dwarfs drifting unseen, glowing very faintly in the infrared, carrying no name and receiving no light. And then there is a population darker still, the rogue planets, objects of planetary mass that have been ejected from their parent stellar systems by gravitational interactions and now drift through the interstellar void with no sun to orbit, alone in the dark. Some estimates suggest that there may be more rogue planets in the galaxy than there are stars. If so, the galaxy is populated by an enormous, uncharted crowd of cold, dark, wandering worlds, drifting between the stars in silence, unknown and unobserved, carrying in their interiors the heat of their formation and perhaps, in the right conditions, geological or chemical processes that could produce environments very different from those we associate with life but not obviously less hospitable to it. The stars we celebrate, the stars we name and draw into constellations and navigate by and worship and write poems about, are the exceptions. The rule of the galaxy is quieter, dimmer, older, slower. The rule is the red dwarf burning steadily for 1 trillion years in a distant arm of the galaxy, the brown dwarf drifting through the dark too cool to fuse, the rogue planet carrying its internal heat through the void between the stars. None of these announce themselves. None of them attract our attention. They simply exist, in the vast majority of the universe's stellar real estate, doing their quiet work in the dark. Proxima Centauri, the closest star to the Sun, is a red dwarf of the smallest and dimmest class, an M5-type star with a mass about 1/8 of the Sun's and a luminosity roughly 1/600th of the Sun's. In 2016, the discovery was announced of a planet orbiting Proxima Centauri within its habitable zone, designated Proxima Centauri b, with a minimum mass somewhat greater than Earth's, completing an orbit every 11 days. Whether this planet has an atmosphere, whether it has liquid water, and whether it is tidally locked to its star, perpetually showing one face to the red dwarf's dim glow, are questions that current technology cannot definitively answer. The proximity of Proxima Centauri has made it the target of the Breakthrough Starshot Initiative, a proposal to send a fleet of tiny laser-propelled spacecraft to the system within the next few decades, reaching it in approximately 20 years at a speed of 20% of the speed of light. The TRAPPIST-1 system is perhaps the most studied example of a red dwarf planetary system. TRAPPIST-1, an ultra-cool red dwarf approximately 40 light-years from Earth, hosts at least 7 confirmed planets, all of them roughly Earth-sized, arranged in a compact system of extraordinary regularity, their orbital periods in near-perfect resonance with each other, the planets tugging each other in gravitational lockstep as they orbit their dim sun. 3 of the 7 planets lie within the star's habitable zone. The system was discovered using a small ground-based telescope called TRAPPIST, the Transiting Planets and Planetesimal Small Telescope, in Atacama, Chile, and subsequently characterized in detail by Hubble, Spitzer, and most recently the James Webb Space Telescope. Whether any of the TRAPPIST-1 planets have retained atmospheres is a question of active current research. Red dwarfs are not quiet objects. Despite their small size and low luminosity, they are prone to powerful flares, sudden explosive releases of energy in their magnetic atmospheres, more intense relative to the stellar luminosity than the flares of the Sun. For a planet orbiting a red dwarf in the habitable zone, close enough to be warned despite the star's dimness, these flares may be a significant hazard to atmospheric chemistry and to surface life. Ultraviolet and X-ray radiation from flares can photodissociate molecules in a planetary atmosphere, and the associated charged particle ejections can accelerate atmospheric erosion. Whether planets around active red dwarfs can maintain atmospheres over the billions of years timescales relevant to the evolution of complex life is one of the central questions in the young science of exoplanet habitability. The far future of the universe, on timescales far beyond any current human imagination, will be dominated by red dwarfs. As the massive stars of the current galaxy burn out over millions of years, and as the intermediate mass stars like the Sun complete their lives over billions of years, what will remain will be the red dwarfs, still fusing hydrogen, still shining in their dim red way, still potentially hosting their planets for trillions of years into the future. The era of stellar life that we inhabit, with its bright blue giants and its brilliant supernovae and its G-type stars warming habitable planets, is, in a very deep sense, the early and dramatic youth of the universe's stellar history. The longer and quieter era of the red dwarfs is the future, a vast, slow twilight, lit by embers, lasting far longer than the present age has yet endured. Dark matter, which appears to constitute roughly 27% of the universe's total energy content, compared to ordinary matter's approximately 5%, does not interact with light. It cannot be seen by any telescope. It is known only through its gravitational effects, the way it causes galaxies to rotate faster than ordinary matter alone would predict, the way it bends light from distant objects, the way it clusters into the filamentary structure of the cosmic web. Whatever dark matter is, and the leading candidates include as yet undiscovered particles that interact only gravitationally and via the weak nuclear force, it is present in the space between the stars, in the halos of galaxies, in the vast emptiness between galaxies. You are moving through it right now. It passes through you, through the Earth, through the sun, through the entire solar system, without interaction, without notice, as though none of it were there. The universe is mostly made of things that cannot be seen from here. Rest in the knowledge of that immense quiet. Chapter 12, The Stars Tonight. Right now, above the roof of this room, the stars are doing all of this. Not in the past, not as a story being told about something that happened somewhere else. Right now, in the present moment of the universe, in the space above the atmosphere that keeps you alive, all of it is happening simultaneously. Protostars are condensing from molecular clouds in the Orion Nebula, crossing the threshold of ignition this very second. In the core of Betelgeuse, helium is burning in a shell around an inert carbon-oxygen core, and the star is pulsating with a period of roughly 400 days in a rhythm that has been established for as long as that star has existed in its current state. In the Crab Nebula, the remnant of a supernova that Chinese astronomers recorded in the year 1054, a pulsar is spinning 30 times per second, sweeping its radio beam across the sky with the precision of a lighthouse. In the local group of galaxies, dozens of supernovae are occurring this year, each one briefly illuminating its host galaxy, each one distributing the elements of the next generation of stars into the surrounding medium. None of this requires your attention. It would all happen exactly as it is happening whether you were aware of it or not. The stars have been conducting this business for 13.8 billion years, and for the vast majority of that time there were no eyes to observe them and no minds to think about what they were doing. They did it anyway. They will do it, most of them, in their million-year timescales, long after any particular eye has closed. Above you right now, if the sky is clear, the stars of your season are arranged in the patterns that the constellations name. Each one is a light source at a different distance, the light arriving at your location from different moments in the past, giving the appearance of a flat plane when the reality is a three-dimensional distribution of stars spread across hundreds of light-years of space. The stars of Orion, which seem so clearly related to each other that they form the shape of a giant's belt and sword, are actually spread across a range of distances from about 250 to 1,500 light-years. The pattern is a coincidence of viewing angle, the human eye connecting points that are, in physical space, vastly separated. Betelgeuse, the red supergiant that marks Orion's right shoulder, is approximately 700 light-years away. The light arriving from Betelgeuse tonight left its source somewhere around the 14th century, around the time of the Black Death, the 100 Years' War, the construction of many of Europe's great cathedrals. The star we see is the star as it was in that era. The star as it exists right now, the actual present state of Betelgeuse, is information that we will not receive for 700 years. And there is genuine uncertainty about what we will receive when that information arrives. Betelgeuse is a variable star, fluctuating irregularly in brightness, and it has all the characteristics of a star approaching the end of its red supergiant phase. When Betelgeuse finally explodes as a supernova, an event that astronomers believe may occur within the next 100,000 years, though the timing is deeply uncertain, it will be spectacular, briefly as bright as the full moon, visible in daylight, casting shadows at night, a pinpoint of light that will slowly fade over weeks and months from a brilliant point to a faint smear and then to nothing visible to the naked eye at all. Whether this has already happened and the light of the explosion is already en route is something we cannot know until the light arrives. The question of when, not when it will happen, but when it happened, is itself a reminder of how fundamentally the night sky differs from what we see in ordinary experience. When you look at a friend across a room, the light crossing the distance takes less than a billionth of a second, and any human intuition about simultaneity is unaffected. When you look at a star, the light has been traveling for years or centuries, and what you see is not the present state of the star but a portrait of it from the past. Look at the Andromeda galaxy, that faint smear in the northern autumn sky, and you see it as it was 2.5 million years ago, when our hominin ancestors were walking upright in East Africa, when the horse had not yet been domesticated, when the city of Rome was unimaginably far in the future. That galaxy contains, roughly, 1 trillion stars, each one conducting its life, fusing, pulsing, orbiting, dying, in the moment that produced the light now reaching your eye. You are seeing a 1 trillion star moment from 2.5 million years ago, all at once, in a patch of sky you could cover with your thumbnail. The stars that are overhead tonight have been overhead every night of your life. The same stars, shifted somewhat by the seasons, the sky rotating through its annual cycle, were overhead on the night you were born, and on the night your parents were born, and on the night of every ancestor stretching back through human history. The oldest star charts we have, Babylonian, Egyptian, Chinese, Greek, describe the same stars in the same positions, visible from the same latitudes, named differently but unchanged. The stars were overhead when the first human being looked up and wondered what they were. They will be overhead long after the last one does so. What they are doing up there is what they have always been doing, fusing hydrogen into helium at temperatures no human technology has yet replicated sustainably, casting their ancient light in all directions at once, living their lives at timescales that make the entire span of human civilization seem like a single heartbeat. They do not know they are being watched. They do not modulate their behavior for an audience. They shine because they are stars, and stars shine, and there is nothing complicated about it beyond the extraordinary complexity of the physics that makes it possible. And the physics is beautiful. Not merely interesting, not merely accurate, but beautiful in the way that only things discovered rather than invented can be beautiful, the beauty of a truth about the universe that was waiting to be found, unchanged by the finding. The proton-proton chain was happening before anyone knew the words for it. The random walk of photons through the solar interior was happening before anyone could calculate how long it took. The cooling of white dwarfs was happening in the dark of the galaxy before any human eyes existed to observe it. The universe does not perform for us. It simply is. And tonight, in the dark above this room, in the cold and silent space that begins where the atmosphere ends, it is being itself, fusing, pulsating, orbiting, dying, being born, without your awareness of it, as it has been for longer than the Earth has existed. The stars are very old, and very busy, and entirely unconcerned with the passage of your night. Light pollution, the brightening of the night sky by artificial illumination, has altered the human relationship with the stars more profoundly than any other development in the history of civilization. It is estimated that roughly 1/3 of the world's population can no longer see the Milky Way from where they live, and in the most heavily lit regions, coastal cities, dense urban centers, the naked eye sky may show only a few dozen of the brightest stars against a permanent gray-orange glow. The International Dark Sky Association maintains a list of dark sky reserves, parks, and sanctuaries around the world, places where the sky retained something of the darkness that all of human history prior to the 20th century took for granted. In these places, on a clear moonless night, the Milky Way stretches from horizon to horizon in a band of light dense enough to cast a faint shadow on white paper. It is the sky as it was seen by every human generation before the present one. The stars have been given proper names by many cultures over many millennia. Sirius derives from the Greek for scorching or glowing. Betelgeuse comes from the Arabic, though its original meaning has been debated, possibly the armpit of Orion, possibly something else entirely, the letters shifted and corrupted over centuries of translation. Vega is from the Arabic for the swooping eagle. Aldebaran means the follower, named for the way it follows the Pleiades across the sky. Fomalhaut means the mouth of the southern fish. These names carry thousands of years of observation and attention, the accumulated looking of civilizations that depended on the stars for navigation, for the timing of planting and harvest, for the marking of seasons and the organization of time. The stars were the first calendar, the first compass, the first evidence that the universe had a structure that could be understood. In 1990, the Voyager 1 spacecraft, launched in 1977, then 6 billion kilometers from Earth, was commanded to turn its camera back toward the inner solar system and take a photograph. In that photograph, Earth is visible as a single pixel of light, a pale blue dot suspended in a beam of scattered sunlight, set against the black backdrop of space. Carl Sagan, who had advocated for taking the photograph, wrote about it: "Every human being who has ever lived, every king and peasant, every act of courage and cruelty, every invention and every error, every saint and sinner in the history of the species, all of it on a mote of dust suspended in a sunbeam." The stars, looking at that photograph, would see nothing. Earth is too small, too dim, too distant from any other star for our civilizations or our conflicts or our sleepless nights to register as anything at all in the observable universe. We are quieter than we know. And perhaps that is the most calming thought available on any night. Not that you are insignificant. Significance is a category that belongs to the human world, not to the universe, but that you are held by the gravity of a planet that has been circling its star for 4.5 billion years without failing. Warmed by a star that will continue to burn for 5 billion more. Sheltered by an atmosphere that took 2.5 billion years to produce and that has been maintained, in approximate equilibrium, by the living world ever since. Embedded in a solar system, in a galaxy, in a universe that operates according to principles so regular and so reliable that they can be written in mathematics and verified by experiment. The stars above you tonight are doing exactly what they always do, not performing it for you, not waiting for your attention, simply doing it, in the cold and the dark, as they have done for longer than the Earth has existed. Right now, above the roof of this room, above the atmosphere, in the cold and silent space that begins where the air ends, all of it is happening. Protostars condensing. Fusion burning. Photons wandering toward the surface. Red giants expanding. Pulsars spinning. White dwarfs cooling. Supernovae distributing the elements of the next generation of stars. And down here, on the surface of the small blue planet that one of those stars warmed into habitability, a person is lying in the dark, in the warmth, in the quiet, listening, or perhaps no longer quite listening, to the sound of a voice describing what is happening above them, in the dark, among the stars, which do not require anyone's attention to continue. Let that be, tonight, exactly enough. Closing, what stars do. The stars are still doing it. Right now, above this room, above the atmosphere, in the cold and the dark and the vast and the silent, they are fusing, pulsating, orbiting, dying. Protostars are igniting. Supernovae are dispersing their elements. White dwarfs are cooling. Red dwarfs are burning, so slowly and so steadily that 1 trillion years will pass before they are finished. None of it needs you. None of it is waiting for you to finish watching before it continues. The universe was old before you arrived, and it will be old long after you leave, and in between it is simply being itself, nuclear and gravitational and luminous and enormous and entirely indifferent to whether anyone notices. Let it be enormous, tonight. Let it be old. Let the stars do what they do, up there in the dark, without your supervision or your understanding. You can let go of it now. You can sleep. The stars will still be there in the morning, a little further along in their ancient work, as steady and as patient and as unconcerned as they have always been. Sleep now. The universe continues without you, and that is exactly as it should be.